5 जणांचं, त्याच्यावरती टाकतो ना
ब्रॉडकास्टिंग लिंक. हा म्हणजे आम्ही
व्हॉट्सअपला.
पाठवा.
तुम्ही व्हॉट्सअप ग्रुपला टाकून द्या तुमच्या.
एक काम करा, तुम्ही फेगडे सरांना पाठवा, ते ऍडमिन आहेत टेलिग्राम ग्रुपचे.
कोणाला?
फेगडे सर.
अच्छा, ते उमेश पण आहे आपल्या ह्याच्यामध्ये, मी शेअर करतोय लिंक. इंटरनॅशनल कॉन्फरन्स. रे सर, जे भाऊ आणि मॅडम आणि बसले ना, तो कॅमेरा फक्त थोडासा खाली करा. हा उमेश, हा बोला ना. हो, 2च मिनिट मी तयार करतोय. होते ते तयार, ते थोडा वेळ लागतो त्याला. 2 मिनिटात पाठवतो. 2 मिनिटात पाठवतो. आणि फक्त भाऊने हे बसले ना तिथं, मॅडमने हे यांचा कॅमेरा थोडासा खाली कर. केला का? अच्छा. अच्छा.
सर तर दिसत नाही यार, तरी घ्या ना त्याच्यात. पण तो कॅमेरा तुमचा तेवढा वेगळा घ्या. याच्यामध्ये मॅडम थोडं तिकडे सर या.
सर काही
हर्षल पाटील सर. हर्षल पाटील सर.
हॅलो, बोला ना सर.
हा, येतोय ना आवाज?
हो, एकदम व्यवस्थित येतोय. रेकॉर्डिंग चालू करतोय मी आता.
हा हा, सुरू करा सुरू करा. धरुण मॅडम. सुरू करा मॅडम. धरुण मॅडम. हर्षल.
हा, बोला ना.
हा, ते जो मैरे सरांचा जो हे आहे ना, त्यांना अनम्यूट कर.
एक मिनिट. केलं. मैरे सर.
Good morning. Good morning, Mananol. Shall we start, sir?
मॅडम,
येस.
एक मिनिट मॅडम, तो कॅमेरा खाली घ्या. संगीता मॅडम तुमचं थोडस. हा, बस बस बस.
Shall I start, sir?
येस, यू कॅन प्रोसीड.
Okay, thank you, sir. Good morning, Mananol. Wishing you a good health and healthy environment in this pandemic situation. Myself, Sangeeta Mule, I feel privileged to welcome you all on the behalf of Chemistry Department, Bhusawal Arts Science and P.O. Nahata Commerce College, Bhusawal, for the International Conference on CPCS 2021. Our college name is being taken with respect for discipline by the parents as well as by the academicians. And this conference is an initiative to ponder over new challenges of research appears in front of us. The conference aims to bring together leading scientists, research scholars, and academicians to exchange and share their research results. It also provides interdisciplinary platform for the research and educators to present and discuss the most innovation, recent trends, and concerns, as well as practical challenges. So the theme of the conference is to discuss the research trends and concerns for the use of science and technology for the benefit of society. And keeping this fact in mind, Chemistry Department, Bhusawal Arts Science and P.O. Nahata Commerce College, Bhusawal, has decided to organize this international conference, CPCS 2021. Now, let's begin welcome ceremony. It is my proud privilege to welcome patrons of the conference, Honorable Dr. Mohan Bhaupala, President of Tapti Education Society, Bhusawal, Honorable Shri Mahesh Bhaupala, Chairman of Tapti Education Society, Bhusawal, Honorable Shri Vishnu Bhau Chaudhary, Sir, Secretary of Tapti Education Society, Bhusawal. I am delighted to welcome Honorable Shri Sanjay Kumarji Nahata, Sir, Treasurer of Tapti Education Society, Bhusawal, and President of today's International Conference inaugural session. And our sincere welcome to Dr. M.V. Vaikora Madam, Principal, Bhusawal Arts Science and P.O. Nahata Commerce College, Bhusawal. I also welcome Professor S.V. Patil, Sir, Vice Principal, P.O. Nahata College, Bhusawal. I also welcome Dr. B.H. Bharati, Sir, Vice Principal, P.O. Nahata College, Bhusawal. I also welcome Dr. A.D. Goswami, Sir, Vice Principal, P.O. Nahata College, Bhusawal. I am delighted to welcome Dr. N.E. Bhangale, Sir, Vice Principal, P.O. Nahata College, Bhusawal. I am heartily welcoming today's eminent speaker, Professor Rajendra Jhope, Sir, University of Texas, USA. I extend my warmest welcome to Dr. Ajay Patil, Sir, Paul Scherrer Institute, Switzerland. Also, I would like to welcome Dr. Vijay Singh Parihar, Sir, Temper University, Finland. I also welcome faculty members, academicians, research scholars, students, and participants who have registered for this international conference, CPCS 2021. So I welcome you all. Now we are commencing towards the inaugural session. Now I request Dr. M.B. Vaikole Madam, Principal of Pionahata College, Bhusawal, to deliver opening remark. Over to you, ma'am.
Namaskar. Very good morning to you all. Our inaugurator and chairperson of today's program, Honorable Sanjay Ji Nahta, Treasurer, Tapti Education Society, Bhusawal, Honorable Mohan Babu, President of Tapti Education Society, Chairman Mahesh Babu Phala, Secretary, Honorable Vishnu Babu Chaudhary, Honorable Dr. V.C. Kolle sir, our guide, our inspirer, our today's speakers, resource persons, all delegates, our vice principals, students, convener of this international e-conference, Dr. Evle sir, and all other members. It gives me an immense pleasure to welcome you all. All academicians, scientists, researchers to the International E-Conference on Changing Paradigms in Chemical Sciences, CPCS 2021, being organized by our chemistry department, Bhusawal Art Science and Pionahata Punamchan Onkar Das Nahta Commerce College, Bhusawal. Our Tapti Education Society, Bhusawal, was founded with the vision of imparting higher education with the motto Vidya Danam Mahat Punyam. The senior college started in 1963 with arts and commerce faculty, and science faculty was started in 1972. Undergraduate and postgraduate courses are made available to this in the campus, college campus. PhD programs are also available in this campus in various departments. This international conference, CPCS, may play an important role for college level researchers and students. This conference is aimed to bring the expertise in various fields of chemistry at college level. The theme areas of this conference include computational chemistry, spectroscopy, green chemistry, synthesis, natural products, etc. I am positive that the International E-Conference, CPCS, will provide the right platform and opportunities for the scientific communities to discuss and share their innovative ideas, which could have direct impact to the society, leading to the ultimate progress of the nation. Once again, I welcome you all, delegates and participants to this international conference. Our today's speakers, our resource persons, are very knowledgeable. Honorable Dr. Rajendra Jhope from USA, Honorable Dr. Ajay Patil from Switzerland, Honorable Dr. Vijay Singh Parihar from Finland. We are very thankful and grateful to our honorable resource persons. Their research-oriented speeches will become very effective for all of you. These speeches will be useful and helpful for your research, further research, and also to design new curriculum. for all the PG courses. I congratulate and appreciate to our chemistry department organizing team who made a lot of efforts. I hope this international e-conference will grant success. Wish you all the best. In the situation of COVID-19, be vaccinated, follow the rules of COVID-19 and stay safe. Thank you. Thank you very much.
Thank you, ma'am, for giving us the insight on the objectives for this conference. On this auspicious occasion, we are extremely grateful to have Honorable Shri Sanjay Kumarji Nahata sir here with us today. I would like to invite Honorable Shri Sanjay Kumarji Nahata sir, Treasurer of Tapti Education Society Bhusawal and President of today's international conference inaugural session to inaugurate this conference. Over to you, sir.
नमस्कार. सन्माननीय व्याख्याते आदरणीय मोहन भाऊ, महेश भाऊ, विष्णू भाऊ, आदरणीय वाइस प्रिंसिपल मॅडम, वायकोळ मॅडम, वाइस प्रिंसिपल सर, पराठे सर, तिरके सर, येवले सर, सन्माननीय आजच्या या ई कॉन्फरन्सचे उद्घाटन झाले असे मी जाहीर करतो. सर्व स्टाफ डे आणि ज्यांनी आजच्या कार्यक्रमाचे अध्यक्ष मला बनवले याकरता मी त्यांचेही आभार मानतो. या कार्यक्रमामध्ये भाग घेणारे कमीत मतलब 150च्या वर पार्टिसिपंट लोकांनी भाग घेतला आहे. सर्वांना या ई कॉन्फरन्सचा उपयोग हो, सर्वांनी त्याच्यात भाग घेऊन आणि जास्तीत जास्त ज्ञानामध्ये आपल्या भर घालावी हीच शुभेच्छा देऊन मी माझे 2 शब्द संपवतो. जय हिंद.
Thank you, sir, for your constant guidance and support. Now I invite Nilima Patil Madam to deliver vote of thanks. Over to you.
A very good morning to all of you. It is a great honor and privilege for me to propose a vote of thanks on this occasion. I am thankful to all the participants for coming to Bhusawal Arts, Science and Purnata Commerce College, Bhusawal, to attend the international conference. We have been fortunate to have some of the eminent persons from academia and the research institutes. I am sure that CPCS-21 will continue to get the generous support from various organizations in the future also. I am thankful to Honorable Dr. Mohan Phalar, President of Tapti Education Society and all the directors of Tapti Education Societies and the Principal Dr. M.E. Vaikole Madam for giving us an opportunity to hold the CPCS-21 at Bhusawal Arts, Science and the Purnata Commerce College, Bhusawal. I am very much thankful to Honorable Shri Sanjay Kumarji Nahata ji. I am very much thankful to Honorable Shri Sanjay Kumarji Nahata sir for sparing his valuable time for inaugural ceremony. I am also thankful to Professor S.V. Patil sir, Dr. B.H. Bharate sir, Dr. A.D. Goswami sir, and Professor N. Bangaya sir, Vice Principals of the Tapti Education Society for their valuable guidance. I am very much thankful to Advisory Committee for their continuous support and advices, which have greatly helped towards the successful organization of CPCS-21. I am also thankful to Professor Rajendra Dope, sir, Dr. Ajay Patil, and Dr. Vijay Singh Parihar for accepting our invitation for this international e-conference. I am also thankful to all the organizing members and the non-teaching staff of Chemistry Department who has greatly helped us for organizing this conference. I once again thank everyone whose contribution has made this conference a successful conference. Now, with the prior permission of President of Session, I declare that the inaugural ceremony is over now. Thank you very much to all of you. Now, next session will be continued shortly.
कॉम्प्युटर आपल्याकडे सुरुवातीला उघडण्यामुळे एक फायदा असा की आपले मॅक्सिमम विद्यार्थी
Good morning, all participants. Some instructions for the participants. During the every lecture session, you will be given the feedback link. So there is no specific time for the feedback link. It may come at 5 minutes. It may come at 20 minutes. It may come after 40 minutes. So you have to fill up the feedback form for every session of the conference, and after the conference you will also be given a oral feedback, so you have to fill that feedback also. So wish you all the very good conference, and take actively participants, ask more questions. These resource persons we have chosen are very diverse fields, so we hope that all the newly recruited faculty will get initiated in the fields. Thank you. Our Zope sir will join us shortly, so it will start within 5 minutes.
Do you see it now? Hello?
Yes, sir.
Yes, sir, visible.
It is visible.
Okay, good. You can hear me well also. Okay.
Yes, sir.
Okay, good. Thank you.
Zope sir, this is Sachin. Before you proceed, we have some 5 minutes protocol.
Okay, yeah, sure. Go ahead. So you see my only one window, right? The presentation window, right? Or you see the whole screen?
No, sir, only presentation window.
Okay, good.
Good morning, esteemed dignitaries and delegates. We have Professor Rajendra Zope sir, University of Texas, USA, with us. Now I request Dr. V.N. Mahire sir to introduce our first speaker for plenary talk. Over to you, sir.
Thank you, madam. Good morning to everyone. Myself, Dr. Vilas Mahire, Assistant Professor at Department of Chemistry, Bhusawal Art Science, Pionata Commerce College, Bhusawal. It is my great honor and privilege to introduce our first resource person, Honorable Professor Rajendra Zope sir. Professor Zope sir has completed PhD under the supervision of Professor R.K. Pathak at Savitribai Phule Pune University, Pune in 1999. After that, he joined as a postdoctoral research fellow at Atomic Energy Center, Grenoble, France. He also worked as research associate at US Naval Research Laboratory, Washington, D.C. during 2002 to 2005. Currently, he is working as professor at University of Texas, USA. Professor Zope is a group leader of DFTSW, UTEP, NRL, MOL, and Flowseek Electronic Structure Code Development Team. His main research area includes chemical physics, development of density functional theory, software development, study of properties of molecules, nanocrystal and materials using quantum mechanical simulations. His current research works involve development and implementation of self-interaction corrections, density functional theory code, which is funded by US Department of Energy Office and Science. Professor Zope has published more than 100 research papers in international journals, having 2,468 citations and 28 H-index. One of his research articles with title Interatomic Potentials for Atom Stick Simulation of the Titanium and Aluminum System received more than 500 citations. I feel happy to share that Sir is alumni of Nahata College, Bhusawal. With this brief introduction, I request Honorable Professor Zope sir to deliver the talk on static dipole polarizability of polysins. Thank you.
Yeah, so thank you for the introduction. I have changed the title slightly. So first of all, good morning to you all. It's 10:30 here in the night, evening. So I changed the title slightly than what was announced to better reflect the content of my talk. I'll be talking about dipole polarities of polyacin as well. So this is a somewhat a broader scope. Okay, so yeah, okay. So this is so I am as it was introduced, I am an alumni of Nata College. I graduated from there in 1989. And I went back to the college in 2018 after almost about 28 years. And this is a picture that we took. That was the time I first met Dr. Yevle. And these are some of my professors. They had just started at that time, very young. They had just graduated and then started teaching. I think I met there R.R. Patil and V.D. Jain. I don't know if they are still around or they have retired. But those were the teachers who have taught me when I was there. This is a picture that I actually copied from the college that I copied from somewhere from the Google. So I can't exactly remember, but I think our classroom was somewhere here at that time. Of course, the college was different that time. We used to enter the college on the highway side, and the back area of the college was open, so we often used to play cricket there. Yeah, so those are the good memories. Since then, after that, I moved to Pune to do my master degrees, and then ended up in doing the PhD there in where I first learned density functional theory. So that was density functional theory was selectively studied. It wasn't as common as it is now. It wasn't widespread like today. So this is my current institute where I am. Our physics department is somewhere here. It's and what you see, these are the buildings. So we are in desert, but the campus is green. And then on the backside, what you see is that we are actually close to US-Mexico border. So the backside that you see here, those homes are in Mexico. It's a nice place to be. It's somewhat remote from the large cities, but it's a nice place to be. Very nice weather. Anyway, okay, so let me start my talk. I work with as I said, my goal is primarily developing the density functional theory and then its implementation in the software codes, which are used to study various properties. We also do some applications, and I'm going to talk about some of those applications, but this is my current team. This is actually a team. This slide is about 6 months, taken 6 months ago. So this is my colleague, and then these are my postdocs. These 4 are my postdoctoral associates in my group. Now, Dr. Yamamoto is become a research assistant professor. And all these are the PhD students. Some of them have actually, Zachary Bushman has just recently moved to Stanford. So this is a group who is actually doing the work, and I, like the professors do, just supervise them. Okay. So here is a brief introduction. I have, since this is a mixed audience with a lot of large percent of the audiences students, so I decided to spend some time in describing the theory behind basics of the theory that we use. So we have. So we use first principle approach. By first principle means without using any empirical parameters. That's also known as ab initio. In particular, we use the density functional theory. So I'm going to explain what that means. But quantum mechanics. So So we do quantum mechanical simulations. It's all quantum mechanics. You use quantum mechanics to predict the molecular properties. And these are also used in designing the materials. So Sachin is using that similar approach for his research. So the basic equation in the quantum mechanics, you say quantum mechanics, you think of the Schrodinger equation. Okay, this is a special case of Schrodinger equation when your Hamiltonian is H is a Hamiltonian there, and when your Hamiltonian is independent of time, then we have the stationary state Schrodinger equation. So if you ask someone what the Schrodinger equation is, you will come up, you usually say H psi equal to E psi, and that's what it is here. This sign is a function of, if you're in the electron system, it doesn't need to be electron, but we are talking about the material chain, molecule chain, which consists of protons and electrons. So these are the position of the electrons. And if you have wave function sign, if you have n electrons, then the wave function is a function of 3n position variable, because each electron you will have 3 coordinates, x, y, z coordinates to describe that. And if you have n electrons, then you have 3n coordinates to do. So wave function is a function of 3n coordinates. And then you have this Hamiltonian operator. Okay, so this is written in the atomic unit. So it simplifies here. You usually have H cross square by 2n here. So this is a kinetic energy operator, kinetic energy of n electrons. This is the interaction of electron with the nucleus, which is actually what holds acts like a glue. And the remaining, this term is the electron-electron interaction. Okay? Yeah, without these two terms, the system will not exist. Okay, so if you had only one of these, if you had only the second term, and if you didn't have this term, then everything will collapse to a point. Okay, so this is simple basic electrostatic that you learn maybe in the second grade or maybe in the third grade. So I'm sorry that this cursor is mouse is very sensitive. Okay, so what we do, we use, so quantum mechanics tells us that if you solve this equation, then you know the wave function of the system. That's a postulate of the quantum mechanics. And if you once you obtain the psi, that's a wave function, you have all possible information about the system. And that's the fundamental postulate of quantum mechanics, and it has its most successful theory. It hasn't failed. And we have the theory for more than 100 years now, and it has not failed. Okay. So the problem, however, is that solving this equation is not possible. Some of you may have solved this equation depending on where you are. So usually I have a physics background, so we did solve this when I was in a third year BSc in the quantum mechanics course. I'm not sure at what point you solved it in chemistry. Yeah, so for hydrogen atom, we can solve it. It's a 1 electron system with a proton and electron. So what you do, you split the system into, because you have a spherical symmetry, the distance between the electron and the proton only determines the Hamiltonian. Okay, it doesn't depend on how far, what the angle is. It depends only on how far the electron is from the proton. And then we can solve this equation. You use the method of separation of variables to separate r theta phi, and then you solve it using your standard differential equation. Okay, so that's how we solve this. But if you have more than 1 electron system, then the things become complicated. Okay, so suppose, how do you describe the wave function? Let's suppose you describe the wave function on a grid. Okay, so you have a set of points in the space. So let's say you take a 2 by 2 grid, 2 by 2 by 2 grid. So even if you take this is a very, very coarse grid, very, very rough grid. Okay, these are just the points in the space on which the function is tabulated, right? Yeah. When you are using a graphic, any graphics, that's what is done inside the code. So if you want to specify one electron, then you have basically 8 points. Okay, because 2 to the power 3 is 8. But if you have just 100 electrons, then you have 10 to the power 90 points, and this is just to store the one wave function. Okay, they are Hamiltonian. You have to write the different terms the Hamiltonian. So the problem is, you can see that we cannot solve this many electrons or equation. The problem is hopeless. So therefore, there are ways to solve this. Even the Schrodinger equation is a quantum Monte Carlo approaches, but that's not what we are going to talk about. So what we use instead is, instead of using a three-dimensional wave function, you use the density functional theory, in which the basic rule is the ground state electron density here, which is shown here, it plays the basic role. Okay, it plays the same role as a wave function does in the Schrodinger mechanics or quantum mechanics. Okay? So what does the wave psi play is in the quantum mechanics? It contains all possible information about the system, and if you want to find any information, all you have to do is take the expectation of the value of the corresponding the Hermitian operator corresponding to the physical observable that you are interested in. Okay, so in this case, we are instead of that complicated psi that you have here, I think the PDF, when I converted in PDF, there are some issues. So you have only the 3 in electron density, which is a function of 3 n coordinates. It's just a function, three-dimensional quantity in the space. Okay, so in conceptually, it is a remainder simplification. So now your energy is expressed, this quantity that we had here on this, the expectation value of this operator, which is this, he is in density functional is expressed in this fashion. Okay, and this is the standard kinetic energy. This is the energy of interaction of electron with the nucleus. This is the interaction of the electrons. This is the classical interaction electron. So electron interacts with each other in a different mechanism. So we know that the electrons have charge, and the charges repel. Okay, because they are same charges. So these charges repel. So this is a classical Coulombic interaction that we learn in the simple electrodynamics or electrostatic course, right? And then the last term is what we call the exchange correlation energy. So electrons not only have the charge, but they also have spin, right? You know, up spin and down spin. Actually, you can have angled spin also, though, in some cases, but let's not worry about that. Okay. So what happens is, if you have an up electron spin, this interacts with all the electrons which have up spin. Okay, so these 2 electrons, if they are up spin, they cannot come close to each other. So if I have an electron here, then there is a hole around it. There is a region around which is devoid of an electron of the same spin, and therefore you have the hole around this. So this hole, you can think of the exchange energy, as the energy of interaction, because due to these electrons and the exchange correlation hole, exchange hole. Okay? Likewise, you have the correlation hole also, which is the interaction of the up electron with the down electron. Okay? So this energy is the pure spin correlation in a way. Okay, and this is a purely quantum mechanical effect. So what we have done is, as you can see in the next slide, maybe. Okay. You have, so we have cast the wave function, we have cast the Schrodinger like wave function into an alternative problem in which you solve solve for the electron density, which is much simpler to, at least dimensionally, it is only three-dimensional, and then it's also physical observable. You can observe it in the experiments scattered through the X-ray scattering. Okay, so this is a main electron system where you have electrons are interacting with each other instantaneously, and this is how you would if you solve it if you look at it from the Schrodinger mechanics point of view or a quantum mechanics point of view, it will look like this. So this problem, instead of solving this problem, what was done in DFT, which is usually, there are different flavors of DFT. but DFT is almost synonymous with the Kohn-Sham formulation of DFT. Okay, so what is done in this formulation is, instead of solving the problem where each electrons interact with each other in what you do is you forget about the real system. You look at the system which is in which the electrons do not interact with each other. Okay, so they interact with each other but through a common potential. Okay, so you have basically a non-interacting system in which the electron interacts with each other through a common potential, as shown here. So you have a single potential, we call it effective potential. Okay. Again, these are, in a strictly speaking, these are not even electrons. These are some quasi-particle, but they behave like almost, we can treat them like electrons. And therefore, and what happens is now, because you have a single potential, now you can split this equation into multiple set of equations. That is done by using the variational principle. We don't need to worry about that at this point. So these two systems, one thing that these two systems are common is the electron density, ground state electron density of this system is same as the ground state electron density of this system. And then you solve, you have your Hamiltonian simplified, and you solve this Hamiltonian. Okay, solve for this Hamiltonian. This leads to, when you minimize the energy, this formalism, it leads to the set of equations which are like this. Okay, these are known as Kohn-Sham equations. Okay, so the potential that I was talking about here, the effective potential here. Sorry, this mouse is very, very sensitive. Okay, so this effective potential that we can again split into the various terms, and which is what is written here. So okay, so this is written as a sum of different contribution. Okay, now what we have is, instead of solving a one complicated equation in the Kohn-Sham theory, we have, if you have n electrons, you solve the n such a differential equation. Okay, these equations are coupled equations, so you have to solve them simultaneously. Okay, so that's basically how the DFT works. Okay, so solving for a many electron system, it boils down in the Kohn-Sham theory to a set of equations, solving a set of equations which are one particle equations. Okay, even having said that, this is still not easy to do. We cannot do this because we do not know the form of the exchange correlation interaction. What is the spin interaction? So those need to be approximated, and this is where depending on the accuracy of this approximation, the accuracy of the your DFT simulation will vary. Okay, this is one factor that determines. There are many other factors. Okay, numerical implementations. But this is what the theory limitation, that the approximation of this exchange correlation determines the accuracy of the model. Okay, it's a theory. In principle, it's an exact theory. Okay, so what do you do? How do you find the approximation? So there is a simplest approximation is what we call the local density approximation. It was actually it was first developed in the crudest form. It was developed by Dirac, Paul Dirac, one of the smartest physicists. So the Dirac actually used what we call as a very simple dimensional analysis to arrive at the exchange correlation form, form for the local density approximation of the exchange. Okay, so what you do there is in this case, actually, you can think of this. I'm making things very simple. In practice, they are very complicated. But you can apply particle in a box model that you learn when you learn first order mechanics, right? You learn that you put a particle and you trap it. We have a free particle. You trap it in the box, and once it is trapped in the box, the particle is still free in the box. But now you have these boundary conditions have changed, so the energy gets discretized. Okay. So you use some sort of this model, what is called the uniform electron gas model. So instead of saying the homogeneous electron gas like you would have in an electron system, right? Yeah. So you even look at the simple, say, let's say carbon hydrogen bond, right? CH bond. So you will have the density piled up in the part of the region and then depleted in the other region, right? So it's far from uniform. Okay, so wherever you have the atom with the larger Z, the density will pile up. If you have covalent bonds, there will be density will also pile up at the center of the bond and so forth, right? But what is done in this model is you just assume the electron density to be uniform and then apply the particle in a box-like model to arrive at this expression. Okay. So these are the various people who contributed to this expression. They arrived at this expression independently. The Gasper and Kohn-Sham, they obtained this using variational approach. Others use some intuitive approaches. Slater used what is simplified the Hartree-Fock approximation to arrive at this. Anyway, I forgot to mention that this Kohn-Sham is Walter Kohn is what gave he received a Nobel Prize for developing this theory, a very ingenious one. The entire the material science, even the chemistry, now chemistry simulations are dominated by the density function theory. Okay, so it was quite ingenious of them to come up with such a theory. So I have had the opportunity to see Walter Kohn. In fact, I was giving a talk in my first talk in the large meeting, in the EPS meeting, that was in 2005 in Los Angeles. And when I was giving a talk, Walter Kohn walked into the room. And of course, I knew him, and then for a moment I froze. Well, it wasn't apparent to say, thankfully, but well, he stayed there for about 5 minutes and he left. But then, yeah, so Walter Kohn was once in my audience. Anyway, so how do you solve these equations? So you can remember I said that these equations are coupled equations. Okay, so this is what the Kohn-Sham equation looks like. This is the del square V effective, that's the potential I was talking about, which is expressed like this. And these terms here, these depend on this density rho. Okay, so the potential here depends on the density rho. And this density, as you can see here, you see my cursor, right? And when I move the cursor, you see it, right? The pointer. Hello? Well, I'm assuming that you are there. Okay. So your density, so you have this differential equation, and in which this density, the effective potential depends on the density, and this density depends on the solution itself. Okay, so rho is depends on psi. So you have sort of a chicken and egg problem. Okay. So you solve. You have to solve solve these equations in what we call the method of successive approximation that you may have learned in math at some point. Okay, so you have to solve them iteratively. You have to make an initial guess, and then you repeat this, solve this equation in an iterative fashion. Okay, so this is enough about the theory. So let's look at where do we use this. Okay, so I've taken 2 examples. I did not mention this to Sachin, but this is one of the area that we work in, and this is the organic photovoltaics. Okay, so we are going to use the theory that I mentioned. Those are have implemented into the codes, and it requires quite a bit of knowledge of math. You need to be very good in mathematics. You have to be good in programming. You have to be good with the not only programming, but you have to be also good at the high performance computing. Because these calculations are very expensive, so you have to solve them on the supercomputers. Anyway, so this is one of the area in which we work. This is the organic photovoltaics. What you see is a schematic. So what are the photovoltaic devices? We use them to convert the light into the electric signal. Okay. So you have the silicon solar cells, for example, standard solar cells. Silicon solar cells. So these are organic solar cells. So what you have is these are two different types. One is a bilayer device. So you have basically a layer of donor and acceptor. So you have the donors are the ones which give away electrons. Acceptors are the ones which accept the electron. And then if you connect those, so if you have say one molecule, so you have two molecules. So this is a donor, let's say, okay. So this gives the electron and to this one, and then you have the electron transfer to this. And if you can pull this electron out, then you have converted the excitation into the signal. Okay, so what is this material? In this case, the material is a built heterojunction. It's a mixture of molecules. Okay, so what is the process? Okay, so the process is like this. So suppose these are the energy levels of molecules, and these are the energy level of another molecules. Okay, so this one is a donor, and this is an acceptor. So what happens is when the photon comes, when the light comes, okay, light is basically a string of photons. This photon excites an electron from one of the occupied states to the unoccupied state. Okay. This excitation depends, of course, on the energy of the photon, but it also depends on what we call the selection rules. Because this transition has to be dipole allowed, but let's not worry about that. Let's just try to understand what the process is. So the photon is coming, and then it excites an electron. It's absorbed by the molecule, and then it excites an electron to this unoccupied state. And if you have another adjacent molecule in which the levels are arranged in such a way as shown here, then this excited electron can migrate to the LUMO of this. Okay, so what has happened? So you had an electron in this state earlier. This electron has now transferred to this state through the process of this excitation, right? So this is called the charge transfer excitation, because the transfer is because it transferred from the donor to the acceptor. Okay, so you have a hole here. Hole is the absence of electrons. You have a hole here and the electron here, and this hole and electron, they form what we call the charge transfer exciton. Okay, so you have an exciton is a bound pair of electron and the absence of electron, which is a hole. Okay, yeah, and then if you can break apart this exciton, then you can that can result in the current. Okay, and that's the idea of. So it turns out that I'm skipping the details. It turns out that the open circuit voltage, okay, so of this cell, if you construct the like a battery from this, the open circuit voltage of that battery, it turns out in this process depends on basically. Well, okay, so the open circuit voltage in this case depends on the difference between these two states. Okay. So therefore, and what is the open circuit voltage? So for students, if you take just a battery cell, then if it's not connected to the circuit, then the difference between the potential, let's say I have this battery, okay, this is a battery, then the difference, this is the top end, this is the bottom end, potential difference between these two is the open circuit voltage. Okay. If there is a potential difference, then we say that the battery is active. If the potential at this point and potential at this point is same, then the battery is dead. Okay, because then it cannot drive the electrons. Okay, there is no force that the electron will not experience force and they will not move. So this is the process. Okay, so we use this. So we develop a theory to calculate the excited states, because this is an excitation process. A description of this excitation process is not trivial. Standard theories fail. So we have developed this method to describe this. I'm not going to what we call this a perturbative delta SF excited states approach. And then these are the details. You basically use the perturbation theory. You define a perturbed Hamiltonian, and we use a first order perturbation theory to find this. Okay, energies. Anyway, so we applied how well our theory works. Okay, so we applied this to the TCNE hydrocarbons. These are the TCNE is some molecule. I think so most of you are chemists, so you know it better. Okay, and then so what happens in this? I was talking about. I was telling you about one molecule is a donor and other is acceptor. That's what it is. So one of these absorbs the photon, and then that absorbed photon is then transferred to the another molecule. They are not bound. They are just they are bound in the same. They are van der Waals bond. There is no direct bond. Okay. So these are actually a model system. This is the kind of system that you will see in the forward lines cells. So you have you put it on the surface, some surface, you take a surface and then maybe a copper one or whatever surface, and you deposit them. Okay, and that's the so how well our theory works. So I'll just show you the results. Okay, so these are some of the model systems, and this is actually quintessence 660. These are the real systems. So this is a singlet excitation. Let's not worry about what the singlet excitation is. We have two different types of excitation: singlet and then the triplet. Okay, so it depends on if the excited electrons flip the spin or not. Okay, so our theory gives this number 3.10, and then this is the experimental number is 3.19. So agreement is fairly good compared to the errors that are produced by the other theories. So what's the big deal? Okay, we did theory one. So if you have a theory like this, or if you have accurate enough theory, not just our theory, any theory you can. Okay? If you take a theory and it is sufficiently accurate enough, then you can use what is called the genome-like project. Okay, so where you basically do a lot of combination of on the computer, you do a lot of combination of molecules, and then find out what are the best optimal pairs, so that will give the largest open circuit voltage. Okay, so these are actually the projects. So the idea is this kind of projects are called material genome project, where the idea is to do an extremely large scale calculation to identify the promising system that can be then synthesized in the laboratory. Okay, so this is one problem that we have been pursuing. These are the real systems again. So this is what is called a light harvesting complex. Okay, this complex is actually exists. So the reason you have this, the plants have green color is because of the chlorophylls, right? So what you see here are the chlorophylls actually. This is the chlorophyll, and you have a bunch of them, and then they are connected. So you see here they are separated from each other, and they have some tails, right? So these are the porphyrins, so what we call the porphyrins molecule, and they are the ones which, so we have learned what is the photosynthesis process. The light is absorbed and then that is converted into the energy by the plant, right? That's what it is here. So the photons are absorbed by this. And then what happens is these are same type of molecules. All of this is a ring, okay? And inside that ring is this molecule is actually sitting here. It's called the reaction center. So all these molecules, they absorb photons, and then this exciton, which is formed, is then transferred through this series of molecules to the center. Okay, so it is here that the absorbed exciton is broken into the electron and hole. So this is where actually the energy conversion happens. These are just the antennas to absorb. These are antennas that absorb the photons. So these are like to improve the efficiency. Okay, so this is a nature harvesting system, and the pointer that I'm making here is these are about 2,500 atoms, and this is about 840. So combinedly, they are about 3,000 atoms, 3+ atoms. And our code can simulate that. That's something that itself is a different story. Designing a code that can simulate a very large system is extremely challenging, because you have to manage, you have to have a good knowledge of memory management in the computing, and then you have to have good knowledge of parallelization paradigms, so to make use of supercomputers. But that's a different story. So this is one molecule which shows another molecule that is synthesized in the lab to mimic this process. Okay, So in this case, these are the antennas. This is anthracene. These are the different chromophores. They absorb the photons, and these photons, then the absorbed photon results in the electron-hole pair, which is an exciton, and that exciton is transferred to this site. And this is where this is a C60 fullerene. That's a carbon buckyball, football made up of carbon atoms. Okay? And this is accepts and serves as an electron here. So there is a charge transfer happens here. Okay, this is actually made in the laboratory by the group of scientists at Arizona State University. This is also another one. This is again a C60 here, the porphyrin here. This is surrounded by water because it's in liquid. And then you have this tail is a beta carotene, is a vitamin A. So here again, this is the same molecule that you have here. This absorbs the sunlight photon, and this photon then is migrates, the electron from that excitation migrates to this, and then you have the hole that is migrates to this. So you have created the charge transfer. Your hole on this part, your electron on this part. Now if you could pull them apart, then you have the current. Okay, so these are the model system that we have studied. Our simulation, our theory that we have proposed can predict this, can give the accurate exciter state for these systems. Okay, and the next is okay. So this is just advertisement what our code could do. This is the largest system that we have studied. This biological polymer. This is a water ball. There was no motivation to study this system except for testing the capability of our code. So we were able to simulate the system as large as 11,650 atom. These are very few people can do that. Anyway, so now I'm going to talk about some more recent problem that we have been studying. This is a very important problem in density functional theory. All density functional calculation, no matter who has done them, they suffer from what we call self-interaction error. Okay, and that is because when we approximate the exchange correlation, in those approximation, these self-interaction of the electron. What is self-interaction? The electron interacts with itself. Okay, this is not. It doesn't happen in real nature. It is an artifact of the approximation that we make that are used in density functional theory. And we are working on the development of theory that will eliminate it. So what are the consequences of that? So these are the two systems that every one of you should know, the students as well. This is an energy density functional, and this is simple hydrogen atom. Okay, so we have solved the hydrogen atom in a quantum mechanics course. We know that if you solve the Schrodinger equation for the hydrogen atom, we get an energy. It's 13.6 eV. Okay, in the electron volt, it is 13.6 eV. If you write it in the atomic units, which is what we are using in this on this talk, it comes out to be 0.5 Hartree. Okay, so 1 Hartree is twice the energy of the hydrogen atom. Okay, so what are the consequences of the approximation? Let's see. So this is something exactly, we know that because we can solve the hydrogen atom exactly. And as I said, we have done it in the quantum mechanics course, and that's a 0.5. But if you use the approximation, such as say, for example, the local density approximation I mentioned. Okay, so what happens? The result that you get is something like 0.2. Okay, so this is significantly destabilized. And the reason is the self-interaction, because the electron interacts with itself. And because of that, the potential seen by this, okay, by electron should be -1 by R. Okay, it's actually -z by R, where z is the charge of the hydrogen atom, but there is one proton. So you can say it's 1 by R as it goes to the infinity. But it turns out that it's not just for the hydrogen atom. Even if you take any more complicated finite system in the asymptotic region, which means we are very far from the system, the potential seen by the electron is -1 by R. This is in real life. In practice, the approximation changed that story, and as a result of which your excitation, the energy levels are wrong. And if you are computing the properties that depend on this quantum thing, their properties are inaccurate. Okay. If you are interested only in that energy differences at the ground state or the equilibrium properties which are there and happen at the minimum. So here, so this curve is basically the H2 plus. Okay. So this is the simplest multi-atom system that we can come up with is a hydrogen atom with a single electron. Okay. Sorry, two hydrogen atoms with a single electron, that is H2 plus. Okay, that's what it is here. And you can see that. So what you happen if you take H2 plus, okay, you have one electron now, and then two protons, and now if you pull these protons away from each other, okay, so you're increasing the separation between them, or in other words, you are increasing the bond distance, bond length. Okay, what should happen if you take them far off? You should have an electron on one, and then the proton here, right? So you have one hydrogen atom, and then just proton. But that doesn't happen in the most this functional approximation. What happens is half an electron goes here and half an electron goes here. Okay, which is not correct. And this is again a consequence of self-interaction error. So we are working on the correcting this method. I'm going to skip it because I think I'm going quite slow, so I'll skip some. But this is how you saw correct for it. Okay. So what you do is, if your DFT energy, then you subtract this self interaction, which is shown here. This is a this is Ni is the electron density of a single electron. Okay. So this is the Coulomb energy of the electron due to interaction with itself. Okay. Oops. Where did it go? Yeah. And that is what we are subtracting out. Likewise, we subtract out the exchange energy of the electron with itself. And this leads to this equation, but these equations are now complicated because compared to the standard Kohn-Sham equation, because now you have an additional potential, which is in which the electrons, which has the orbital dependence. Okay, so so then it's all something which is complicated becomes even more complicated. But anyway, so what we have done here is I'm gonna to skip something for the sake of time. So what we have done here is we introduce a new method. This is very recent work, which is published 1 year ago, and it is very high, well received. This was editor choice. This was also highlighted by Department of Energy, which is our funding agency, as a scientific breakthrough. Okay, so what we do here is we look at the main electron system. Here is shown as a benzene, or here is a krypton atom. Okay, so conceptually, what we do, mathematically, it's complicated, but conceptually, what we are doing is, if your main electron system, we are looking at the regions in the main electron system in which the electrons behaves like as if it is a single electron. Okay, so these are called the one electron regions. So this is what you see here, the one which are in yellow. These are the one electron regions. So this is wherever this yellow is. These are the one electron region. Okay, and then we apply this correction that I showed you only in those regions. Okay, and this turned out to be quite effective, remarkably accurate. So here I'll show some results. Okay, so if I'm going back to actually. Oops. Sorry about this. My mouse is very, very sensitive, so I have to. I'm going backwards. Yeah. So equation wise comes out like this. We are basically, this is the factor that identifies where are the one electron region. Okay. And then we apply the correction here. So, and as I was said, this was considered as one of the most influential paper in 2019. It's also is a basic highlight of the Department of Energy. Okay, so how does it, well it works? So this is the atomic energy. It's for various Z's. And here you see this is the local density approximation. And this is the Purdue-Junger self-interaction correction. And this is where you have, this is our approach, okay? In terms of here, the bar, it's the same information here, it's in a bar graph. So this is where we are, okay? And this is only using LDA. So you apply the correction only to the LDA and local density approximation, and it's very accurate, okay? So atomization energies, what are atomization energies? The amount of energy you need to supply to break the system into the components. Okay? And that energy is basically also quite accurately predicted. Okay. Reaction barriers, these are important in catalysis, catalytic processes. So here again, these are the error bars using different approximation, local LDA, PBU scan, then these are various SSE scheme, and this load scheme. So this is also comes out very accurate. Okay. And okay, so this is the final topic. Okay, so we have a theory that works very well, and then we are applying it to this system now, which is to study the dipole polarity of polyacid. Okay, so these are the benzene, naphthalene, anthracene, tetracene, pentacene, and you can go on by adding this more and more ring, hexacene, and so forth. Right. So what is the problem with this? Okay, why you need the self interaction in this system? The reason is that here. So if you suppose you take a chain of atoms, and if you remove, these are the chain of hydrogen atoms. Okay, so the room you are in, you have hydrogen atoms, and they are sparsely separated from each other. So now if you remove an electron from it, okay, so the atoms are non-interacting, they are far from each other. The electron should be removed from one single electron atom, right? But in DFT that doesn't happen. That electron is removed from all the part of the electron is removed from every single helium atom. Okay, so if you ionize the helium atom in your room, that's what would happen in a theory. I'm somewhat exaggerating this, but what would happen in this point was a very, very small fraction of the electron will be removed from this. And this is actually what the simulation show. And the reason is that because the hole that is left behind after removal of electron is delocalizing in this method. So this is the same information that's it. So if we apply these are the equations for calculating the polarizabilities, you basically have to find this second order derivative of energy with respect to the applied field. Okay, what's the polarizability? Put the system in the electric field, that applied electric field will polarize. Okay, so the positive charge will, the positive, if you have plates, two positive plates, this is positive and this is negative, the electrons will move, and there is a system in between, the electrons will move in this direction, and the protons will move in this direction. So you have the polarization, and that polarization we can expand in the Taylor series, and that's this is the photon polarity. We calculate using the finite difference. Okay, so so these are the results from the different approximations, and how well our approximation works is, again, this is the one, and it works quite well. Okay, and the reason is because this electron delocalization I was talking about, that is arrested in our method. Okay, so this is another topic I'm not going to mention much because I'm almost out of time here. So this is, we also applied our theory to look at the cluster water cluster anions. So these are the systems that are probably of interest to Sachin, so I added this. So here the question that has been so Sachin comes from the chemistry community who think that the DFT is useless. The community think that the DFT is useless for studying this kind of system, and that expectation, that is true because the previous approximations are not accurate enough. Okay. And the reason is again the delocalization error that I was mentioning. However, if you use the correction, the new correction that we have developed, this LC, you get these these are the what we call the vertical detachment energies, that the energy required to remove the electron without relaxing the geometry. So you think of it as you have a system, water anion, and you shoot the electron with a laser gun, so the electron is knocked off instantaneously, right? So those are the energies that are calculated, and this is the error with respect to the gold standard method is 17 MeV. Okay. So this is why this paper was actually, this was also the hot paper of 2020, which appeared on the front page of PCCP. Okay. So basically, I'll conclude here. So basically, what I have shown you is that the distributional theory can be used to predict some properties. I talked about the some properties. There are many properties you can predict with the density functional theories. Okay, and depending on the kind of property that you are interested in, the theory can be accurate. But typically, if you are interested in the property that involve a non-equilibrium, like where the bonds are stretched, so it's like breaking the bonds, then density functional theory doesn't perform well, and this is where you have to use these SIC corrections. So that's what we have developed, and it works well. Okay. So this is once again, this is a picture of my team before we were getting ready to go to Denver to attend American Physical Society's meeting last year. This was just before the pandemic began. So thank you. Our research is supported by Department of Energy. And as you see the composition of the group, we have students from all over the world, all over the faiths. We have, I mean, all religions. We have people from Nepal, this is Bangladesh, these two are from Bangladesh, Mexico. This is US, this Yo is from Japan. Peter is from Nigeria. Kohao is from Taiwan, and Carlos is American. So anyway, so I have one thing that I wanted to say that if you are interested, if you have like programming, if you're good with computers, or at least you have the willingness to learn that, you can write to me for a PhD position. I usually have at least one PhD position per year. Okay. So this is for the students. Okay, and I'll be happy to take questions if you have any. You hear me? I kept talking.
Yes, sir. Yes, sir.
Okay, good. Yeah, if there are questions, feel free to ask. Either you can type in the questions or you can speak up. I don't know how you handle them.
Sir, I have a query regarding this SIC DFT.
Mm-hmm.
How does it perform for the diffuse anionic system?
Actually,
specifically ionic liquids.
Yeah, so these are, where is this? These are diffuse anions. So the electron is actually, these are dipole bound anions, right? So the electron is unlike the standard anions. For the standard anion, the electron affinities are in eV, like maybe 1 eV or so. For this system, the electron affinity is very weak because the electron is far off actually from the on the system. In fact, for a single water molecule, you cannot add an electron, right? But if you for dimer, you can. So these can describe dipole bound anions, which are the weakest anion we have. Okay, the problem is this. These are, if you want to describe this kind of system, okay, so the theory has a correct behavior in the asymptotic limits. That's why it can describe. And then you need the extremely large basis sets to describe the systems that because the electron is diffuse. And if you use a very, very large basis set, then you have the problem of linear dependencies. The basis set become linearly dependent. So the calculation becomes somewhat challenging, but yes, theory can describe this weakly bound electrons. Okay, and, I don't know ionic. You said something about the ionic liquids, right?
Yes, because their interactions are very strong. We can call them as a strongly correlated systems.
Yeah, so I think SIC works well. So I did not show this to you, but if you have the He2 plus, right? If you take He2 plus and pull it apart again. So take a helium dimer and with the one electron, remove the one electron, and now you start increasing the bond distance. The density functional theory methods fail there. But SIC, this SIC works well. So my answer is it should describe. So we have not done anything beyond He2 plus, but we expect this to work SIC. So people use this kind of like a Hubbard model and what else they use? Well, the DMRG and those kind of techniques. I think this should do. SIC is expected to work in those cases. The problem is with us, it's not the problem as such. We will solve this because the theory is new, so we have still, there are some, so here in our approach, we use what we call the Fermi-Laudin orbital because we have to use the localized orbitals here. Standard orbitals that you get by diagonalization cannot be used. We have to use the what we call the unitary transformation to localize the orbitals. Okay, so that's an example of local orbitals. It's what you use NBO, right? NBOs probably you are familiar with, natural bond orbitals, right? Those are the local orbitals. So you have to use that kind of orbitals for this system, and that makes the unitary. And you have to use special type of orbitals so that the unitary invariance is not broken. We use Fermi-Laudin orbitals. Yeah, but to answer your a simple answer is that we expect this to work for those systems, strongly correlated systems. Where it may not work is if you have the you have this multi-reference character, then there it may not work because it's still single reference area.
Okay, thank you, sir.
Mm-hmm.
So any more questions from audience? You can send out your questions in the chat box also.
It's actually better in the chat box if the audio, if there are audio issues.
If there are no questions, then let us thank Professor Zope for his valuable time and guidance and oriented us towards the newer development in density functional theory. So thank you very much, sir, for your precious time.
Thank you. I'll try to attend one more talk, but it is already 11:30 here, so I'll probably attend. I apologize to the speakers, but I will attend one more talk and then I may leave. Okay, so
okay.
Thank you again. Thanks again for your invitation and your attention.
Thank you, sir.
Bye-bye.
Thank you, sir, for sharing your great knowledge with us. Now, the next session will start shortly. Please be with us.
मॅडम हॅलो हॅलो
Hello.
हा नेक्स्ट सर जॉईन झालेले आहेत विजय सिंग सर
Yeah.
परिहार सर.
Yes, please
Join the
enable
lecture.
me to start
Oh,
my
oh.
video if possible. Beginning.
वेट सर.
Hmm. Hello. Hello.
हॅलो सर येतोय
Yes,
आवाज.
sir, you are
Ah,
audible.
yes, yes.
Yes.
So,
Good morning.
good
Now
morning.
it is my honor to invite Dr. Vijay Singh Parihar sir for his thinker words in his field of research. Now I request Dr. V.N. Mahire sir to introduce Dr. Vijay Singh Parihar sir. Over to you, sir.
Thank you, madam. Good morning to everyone. It is my great honor and privilege to introduce our second resource person, Dr. Vijay Singh Parihar sir. Dr. Parihar sir received PhD from Savitribai Phule Pune University, Pune in 2016. After getting the doctoral degree, he worked as a research associate at Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore in 2016, and National Postdoctoral Fellow at Indian Institute of Technology, Indore in 2017, respectively. Currently, Dr. Parihar is working as postdoctoral researcher at Tampere University, Tampere, Finland. During his PhD and postdoctoral tenure, he has served as teaching assistant at SVPU Pune and Tampere University, Finland, respectively. He has several honors and awards to his credit. I would like to mention few of them. He is a recipient of Dr. D.S. Kotari Postdoctoral Fellowship, University Grant Commission of India, TUT Foundation Postdoctoral Research Grant to work at Tampere University, Finland. He has been awarded with SCRB National Postdoctoral Fellowship of DST, New Delhi. He also awarded with Erasmus Mundus Fellowship to carry out research at Uppsala University and Stockholm University, Sweden by the European Commission. Sir is life member of prestigious scientific societies such as Chemical Research Society of India, Society of Biological Chemists, Asian Polymer Association, and the Society of Polymer Association, India. Dr. Parihar has published his research work in scientific journals of international repute. Besides this, he has worked as member of special issue editor for journal Polymers. He is serving as referee for scientific journals such as Micromachines, Frontiers in Chemistry, and Frontiers in Microbiology. With this brief introduction, I request Dr. Parihar to present his talk on the synthetic organic chemistry in the progression of bioconjugation strategies. Thank you, sir.
Thank you for your kind introduction. And it's my pleasure to present some new aspect of synthetic organic chemistry, expanding in the field of bioconjugations and ultimately in the use of tissue engineering and biomaterial development for the next generation technologies, especially the biomedical medicines. So am I audible to everyone, right? Hello?
Yes, sir. You are audible.
Yeah. So now, as you see this, I'm talking today. I'm going to talk about the bioconjugation strategies and the progression of synthetic organic chemistry and bioconjugation strategies. So if you see this structure, the representative structure in the bioconjugation strategy, you can see there are some groups attached to some molecule, which I will tell you later, like some big molecule, polymeric molecules. These are azide and thiol, and these kind of amines and many more kind of moieties you can see here. They are kind of representing bioconjugates group. And if you see the linker, drug development, diagnostics, and research tool. So this means this slide shows the overall applications of this bioconjugation strategy. But in our lecture, we will mostly focus on the linker and drug development and tissue aspect of that from application point of view. Linker means I will tell you later, like why we are calling them linker, because we are going to talk about some small molecule which will be attached to the polymer, biopolymers, and they will act as a linker, and then they will be utilized in the development of biomaterials for the tissue engineering and other applications. So in this lecture, we will mostly focus on the linker development using the synthetic chemistry tool for as a bioconjugation strategy. Yeah. So what is bioconjugation? First question. So bioconjugation is just, it's not a like kind of very different technique. It's just a conjugation of two, like attaching two molecules, conjugation of two molecules. But the condition is this: one molecule should be biomolecules or biopolymers or something. So if you are attaching any small molecule to the big biopolymers or biomolecules, that's called bioconjugation. And mostly in biomolecules are in this case are mostly carbohydrate, protein, or nucleic acid. But in this lecture, we will focus on carbohydrate and protein mostly. We will skip the nucleic acid part here. And synthesis and strategy. But if you see later, like bioconjugation generally involve the conjugation of very small molecule to the biopolymer. So it looks quite simple from the structure perspective. Or if you see the organic chemistry involved, it's very simple organic chemistry. But developing very efficient bioconjugation strategy is very difficult, and it's a challenging because there are so many residues and so many groups in the biopolymers where the selective reaction is very difficult, because there are many other reactive groups, so which we need to protect some groups and then we have to perform. And also at the same time, selectivity and is matter, like getting selective reaction to particular group is very difficult and challenging, which lead to some inefficiency in the reaction. And also there are so many polar molecules on the biopolymers which interfere in the reactions. So that's the reason although it's look simple, but it's difficult to develop very effective bioconjugation strategies. If you see this representative figure here, it shows like many different different chemistries. These are representative chemistry, like amide bond formation, which is quite simple, CONH, imine formation, Michael addition reaction, disulfide bridge bond, click chemistry. This is simply azide alkyne cycloaddition, electrostatic adsorption also fall into the category of bioconjugation. Even if they are not covalently linked, then still it comes under bioconjugation if you adsorb some molecule by electrostatic interaction. Hydrophobic interaction by making lipid kind of liposome kind of molecules, ascimedes, there also comes under this application. Amidin biotin interaction, even this antigen antibody interaction is also comes into this category. So these are like a very broad subject, and attaching these molecules, if you see in the center, like amines, COH, and bringing these uh, uh, functional groups into the biopolymers need bioconjugation strategy. for the various applications. So our aim is to discuss how we can bring these groups to the biopolymers in a very efficient way. That's where the bioconjugation chemistry and synthetic chemistry skill comes. So these are some bioconjugation strategies which we use mostly in our lab. So this in general, there are so many bioconjugation strategies, like so many groups people are attaching to the biopolymers, but these are the main groups which we are like concentrating in our lab. So I would like I thought to include this slide here, that these much more, small molecules we are trying to attach to various polysaccharide, as I mentioned earlier, carbohydrates and proteins. Polysaccharide and protein, we are trying to introduce these small groups. These small groups trying to bioconjugate with the biopolymers, and then later attaching these molecules. We use these molecules as a linker for hydrogel chemistry that we will discuss later. So why we are using this? Why we are attaching this these small molecule to the big molecules? Because as I mentioned, these small molecule will provide us the functional group into the biopolymer, which native biopolymers they didn't have these kind of functional groups to serve the purpose, or if you want to cross link any end application. So we first by using synthetic chemistry, we optimize the bioconjugation strategy. We are attaching a small molecule to the biopolymer, and then we are making the hydrogels, especially because in this lecture I will only concentrate on the hydrogel formation by using the bioconjugate chemistry. So we are then, after attaching this molecule, we make hydrogel, and these hydrogels I will cover the what are the applications we are mostly dealing with here in our lab. This after conjugating these small molecules, so please don't get confused with the hydrogel chemistry with the bioconjugation. So first step to introduce the small molecules, attach a small molecule to the biopolymer, so that's bioconjugation. And after attaching these molecules, our aim is to utilize to develop some hydrogel chemistry. So for hydrogel formation, we need like whether we can develop chemical cross linking or physical cross linking. If it is chemical cross linking, there should be a like kind of proper covalent bond formation. If it is physical cross linking, then it could be hydrophobic interaction, hydrogen bonding, or stereo complex formation, ionic complex formation. It could be anything. It is just ionic interaction or some electrostatic interaction. So these are the broad category of chemistry which involved in the hydrogel cross-linking, but we will discuss about mostly here the chemical cross-linking. So if you see, as you see it in the beginning, like it shows that these cycloaddition reactions, click chemistry, they all are utilized in the bioconjugation. So through bioconjugation, we try to introduce this alkene groups into the one biopolymer, and this azide groups to the another biopolymer, and then we perform this cycloaddition reaction. So two molecule cross link and hydrogel formation. There will be a tight network in the polymeric system, and there will be a lot of cross linking, and they will have some porous structure, and they will absorb the water. So that they form the hydrogel. So these are some strategies. Here we need catalyst because this reaction is catalyzed by copper. But if it is there is strain in the system, the cycloaddition can be performed without using catalyst or so these procedures. So the one kind of necessity of these kind of reaction, they should be bioorthogonal, because uh, uh, hydrogel system we are going to use for tissue engineering, and sometimes we also use in vivo also. So cross-linking chemistry should be bioorthogonal. Suppose in case we are going to make hydrogel inside the wound or in the in vivo system, then it should be bioorthogonal. That means the reaction should happen without interfering the native biochemical process system, the biological system. So this is the kind of requirement. And then if you see here, oxime chemistry, this is another very interesting chemistry where we bring aldehyde molecule to the one biopolymers and oxime to the others, and then we use this oxime formation chemistry. And then in the similar way, if we have NH2CO, then it's called hydrazone, and then it's called hydrogen chemistry, hydrogen formation. We can use that chemistry also for hydrogen formation. And this is simply just a ligation reaction of this thiol and thiol replacement. I mean ester. Thiol ester is a kind of trans-esterification kind of reaction here. And this is typical Diels-Alder reaction, which is also very much used in the hydrogel formation, and because it doesn't need like produce any side products. So this is very good chemistry bioorthogonality point of view. But generally the thing is like these kind of reactions, they need high temperature. That is the one of the drawback. But nowadays people are trying to develop some cycloaddition reaction which could be performed at the body temperature. The research in that direction is. And this is simply a thiol in click reaction, which is initiated by the UV initiator and in presence of UV light. Thiol in chemistry, thiol ion chemistry. This kind of similar chemistry. Only thing is like alkenes and alkyne. This is thiol in chemistry is also very famous, not only in bioconjugation study, but if you see several tagging, molecular tagging is also used in these kind of chemistries. And this is just photocross. This is quite simple reaction. Like if you have acrylate group on one polymer, and if you want to cross link them, just add photo initiator, and you will be exposed to UV light with different exposure time and intensity. You will get the cross linking hydrogel. So this is very common. And nowadays, for especially for the 3D bioprinting purposes, this kind of chemistry is too much exposed, and we are also utilizing in our lab photo cross linkable chemistry for the development of bioink for the modern tissue that we will discuss a bit later. And this is using the kind of Michael type of addition reaction. This is also very much used for the hydrogel chemistry, and these groups are introduced by the bioconjugation strategy. This is also a very much used chemistry in this field. And disulfide chemistry is also very important, especially if you would like to tag some if you would like to label some molecules for some drug delivery purposes, also for the hydrogel formation. This reaction is very important. But the only drawback of this reaction is like this disulfide bond is not very stable. Sometimes it get, if there are some other residues available with the thiol, then this thiol will get exchanged, and then new disulfide bond formation take place. So this has some kind of drawback related to this chemistry. But if there is no some thiol residue in the system, this chemistry is really good. So now we will focus on the application. We will talk about the why bioconjugation is so important nowadays, because this bioconjugation provide a way to develop biomaterials, new biomaterials by introducing some simple functional groups which enable us to make hydrogels, and then they have a brilliant application in the modern tissue. So the most important application nowadays is going on is development of bioink. Bioink means it's a very kind of debatable term. Some people's even pre-hydrogel solution which could be printable, they call as bioink, and they add the cell later into the system. But some people says you should add the pre-hydrogel solution with cells, and when you print this system, this pre-hydrogel solution with cells will call as bioink. And some people even they use the simply cells, very like thick cell or decellularized matrix. They also called as bioink. So bioink is a common term, but here we will focus on the hydrogel based bioink, because here the bioconjugation strategy play the role. But if you simply decellularize, if you are taking the decellularized matrix from the tissue, that will not involve any chemistry. So we will focus on hydrogel based bioink here, which we are also working on. So hydrogel, what is the challenges and difficulties in development of hydrogel bioink? First question. First of all, we should think about the starting material first, because if I would like to develop some bioink for, let's say, for hard tissue engineering. Then I need to select that kind of biopolymers. Like I need to do some study in which kind of polymers, like let's say hyaluronic acid or collagen or maybe gelatin, which material is like known as a good material for the hard tissue, like cardiac tissue engineering. So I have to choose those kind of biopolymer first, and then I have to decide the which kind of bioconjugation chemistry I will need, depending on the group I would like to introduce into the biopolymer. Let's say I want to introduce the acrylate group, then I have to choose that kind of simple strategy to bioconjugation strategy to introduce the acrylate group, and then that acrylate group I will use as a photo cross linking, using the photo cross linking chemistry, and then I need to decide the molecular weight and then their density, because this should be printable also. So developing a hydrogel with bioink is challenging because you need to take care of type of cells which is compatible with that material, and then you have to think about the printability, like how shear thinning properties and their viscosity, whether they are printable or simply it's liquid. And then there you have to target to understand this difficulty. If you see, this graph is like explaining everything. So this is like printability, and this is biocompatibility. This is the bioprinting or biofabrication window, you can say. So if the challenges is like go side and side. So if you try to develop a printability, better printability in the hydrogel, then you sometimes lose the biocompatibility by doing those kind of chemistries. And when we try to improve the biocompatibility, sometimes you lose the printability behavior of printability property of the molecule. So balancing these two properties simultaneously is very challenging. That's where the chemistry plays a role. So we have to select in the chemistry, bioconjugation chemistry so brilliantly that it should give the very printable property to the hydrogel. At the same time, it should not be toxic, and it should be biocompatible with the tissue we are going to grow. So this is the challenge we need to take care. So and to address these challenges, there are some properties that bioink should have. So this should be biodegradable. So again, we have to select the bioconjugation strategy very brilliantly so that it will not affect these kind of like property, like shear thinning property, bioprintability, compatibility, in situ gelations, and permeability to oxygen. This is also a very important factor, like hypoxia and hyper oxygen concentration. So oxygen concentration maintenance is very important. If you see, like recently, like a year back, like Nobel Prizes gone for the research for the hypoxia research. So oxygen concentration play a very crucial role in tissue engineering. We have to take care of so we have to develop the bioink, or you can say hydrogel, in such a way that it should properly, there should be permeability of oxygen into the system so that tissue grows properly. And depending on the bioprinting technology we are using, that also play a role. So we have to develop the cross-linking chemistry should be compatible to the printing technology we are using. So type of printer. So for example, we are using extrusion-based bioprinting here in our lab. So we have to develop the chemistry which are easy to print with this kind of system. For example, photo cross-linking chemistry is very like easy to handle with the extrusion-based bioprinter. I will show you why it is, because as soon as we print and we can like into the printer head, we can like fit the UV system, and then you can print one layer by layer printing. You can print one layer and you expose to UV and it will cross-link. Again, you can print one layer and then expose with UVs, then it will cross-link. So you can develop a 3D structure by this, using the extrusion-based bioprinting, and with the combination of this is a peculiar like process, how it goes, like the kind of cycle, how this whole bioprinting process works. So for example, if you would like to print some part of particular design, so you have to 3D scan and develop a CAD model, the structure which you are going to print, and then that design feed it to the printer, and then printer will print that particular design using this bioink, and then you have to grow the tissue on that, like required tissue. If you want to do bone tissue engineering, then you have to grow the bone cells, and if you want to do, let's say, cardiac tissue engineering, then you have to grow the cardiac cells on that printed structure. And this is a kind of application which is very hot application nowadays. I will explain you later. This is called as body on chip or organ on chip technology, which we will discuss a bit later. So, what is the use of all these things? Well, we discuss a lot about bioconjugation, importance of organic synthetic chemistry and bioconjugation, hydrogel formation, hydrogel chemistry, and we talk about several tissue engineering. So the end application we see here is like by developing these strategies, you can develop a proper bioink which could be printed into the 3D structure, and you can do the 3D tissue engineering. So the future of this 3D bioprinting is you can generate a lab grown organs. So if we can like avoid the donor, we in the future we will not need donor for kidney and bladder and other organs. We can grow them into the cell by using 3D bioprinting technology combining with tissue. And apart from this medical application, there is also concern of meat. So I don't know how many people already heard about this. Lab grown meat is already in the market in some countries like Singapore and some European countries and US. I'm not sure about US, but in many places the lab grown tissue is approved approved and is in the market. So we can avoid the slaughtering of the animal, and we can develop a kind of, it can boost the food industry by lab grown meat. So again, the lab grown meat, we need like bioinks to print, and then we can do the lab grown meat. So this has huge potential in the future food industry as well. Now we'll discuss, as I mentioned before, like what is organ chip and body on chip technologies. This is also related with 3D bioprinting and tissue engineering. This is somehow it's a combination of you can say it's combination of chip technology and combination of very advanced engineering, microfluidic technology, tissue engineering, chemistry. It's a combination of everything, you can say. It need like microfluidic technology, it need tissue engineering, it need chemist, it need biologists. So combining this technology, one can develop this body on chip. And body on chip means it will not be a complete human, it will not be a real human body, but we will have a different chips, and one chips will represent one organ. And we will there in one chip, suppose one chip is, this chip is like heart, this chip is lung, this chip is kidney, and then by combining them with the microfluidic channels, and this when this will work together as a body, then this will call as a body on chip. And this body on chip could be used for the drug testing, and so that we can avoid the drug failure, like drug testing into the human. So like kind of last stage failure we can avoid. So it could reduce the cost in drug development. At the same time, we can use to develop a drug for personalized medicine, that I will discuss in the next slide. So here, suppose if you want to develop some disease model, like let's say if I want to study on some cancer, particular, let's say breast cancer. So I need not to like take work on the actual breast cancer patient, but instead I could develop a breast cancer on chip. That means I will take the cancer cell from the patient, and I will grow into this chip, and I will develop a tumor model here, and then I will test different drugs, and I can easily test which drug is like suitable here. And instead of trying several drugs on that patient, we can give directly that drug which is like most suitable to the patient. So developing these disease model by using organ on chip technology could lead to the personalized medicine in the future, especially in case of treatment of cancer. It will be really useful technology. And this is overall present like representation I showed. Like if you want to, if you want to test particular drug for on patients, so we can take the stem cell from that group and we can grow a body on chip model, and we can like test those drugs, and then we can give that particular drug to that patient, which is more suitable drug for that patient. So we need not to give trials for many drugs, and we can avoid a lot of side reaction in the patient. So this will be a huge development for personalized medicine in the future. So nowadays we the drugs are very common for everyone. If someone has some cancer, so let's say doxorubicin is given to many patients. But if we have personalized medicine, then we can screen the like 50 existing drugs, and which drugs is like most effective into that particular patient. We can give that drug to that patient. That can save many lives. And these are kind of interconnected. I would like to say how they are interconnected, because personalized medicine is connected to drug development. Because as I said, like if there are 100 drugs available for particular disease, then we can test which one is suitable for the particular patient. So it will of course help in the drug development, and also connected to personalized medicine. And if we are developing disease model for particular study, let's say we are developing uh, uh, like brain cancer model into the system, into the chip, then we can study that brain cancer and that can be connected to personalized medicine. Again, suppose if you are studying the general brain cancer for drug development, is fine, it's not connected to personalized. If we are taking particular cancer cell from patient, and then we are developing this disease model especially to treat patient, then it's connected to personalized medicine. So, and this by using this, we can avoid the testing with animal unnecessary. We can directly test the drugs in these body on chip and organ on chip model, and we can avoid the animal testing in the future. That is another. So, in short, to be summarized my like research here, what I actually involving in my lab. In my lab, I'm all first of all, I'm like trying to develop the best and easy possible bioconjugation strategy to develop biomaterials, and to address my end application. I like work on some questions like like can we mimic the nature, because we are mostly working on the biomaterials, and bioconjugation strategies are developed by us, they are artificial, but can we mimic the nature, because nature also do some bioconjugation reactions. Can we mimic the nature, and can we develop a cell environment in the hydrogel which will be similar to the native environment for the cells. So addressing these questions, we are trying to develop some chemistry and biomaterials in our lab. And for example, this like 2 years back, we developed a bioconjugation strategy. So we took biomolecule. This is hyaluronic acid. This, if you see, this backbone was hyaluronic acid. And by using these small molecule, hydrogen molecule and dopamine molecule, this is and then we conjugate by using bioconjugate chemistry. And then we use this small molecule as a cross-linking agent here, develop hydrogel, and those hydrogel we use for the cornea regeneration, so that we can regenerate the cornea in situ in the patient. And we try to develop we try to deliver the stem cell into the cornea in the pig model, and then they were able to regenerate the cornea very successfully. That's a kind of was a big, and based on this research, a big startup started here in this city, and they are trying to develop a tissue engineered cornea here, and soon it will come into the market also. It's quite a huge success here. Especially this lady Laura is like taking lead in this startup where they are developing tissue engineered cornea, and in fact they are regenerating in situ also, in the trying to develop in situ in the patient. Yeah. So as I said, can we mimic the nature? So in this paper, we try to mimic the nature only. This group we attach for the cross-linking chemistry, and this group we attach to produce some kind of natural, because as you see tissue adhesive, because this dopamine give the tissue adhesive property to this molecule. As I mentioned, we are trying to mimic the nature, and if you see the nature, these kind of muscles, they can stick into the surfaces even in the presence of water, because they release some dopamine, and that produce the adhesive, that provides the adhesive property. And so we thought, why not, if we use this dopamine in our system, why not we can also develop the tissue adhesive property. And but since the cornea is like very delicate and it need to have some adhesive property, so adding this dopamine, we were able to get tissue adhesive property into the hydrogel, which helps to regenerate the cornea in situ. This was the first, and then we tried to develop several others, more like bioconjugation strategies, which we are using in for the development of like antibacterial coating and many other applications, different hydrogels here. And this is also on a very recently we developed a photo cross linkable, as I mentioned, like we are also trying to introduce a small, like very simple groups like acrylate group to the biopolymers. These are all biopolymers. We use collagen, gelatin, hyaluronic acid, alginate, or we took all four biopolymers, and we tried to, by using bioconjugation strategy, we introduced these small groups, which is photo cross linkable, and then we cross link them as a hydrogel, and we try to print this, try to do the bioprinting. So we were successfully able to develop these photo cross linkable bioink, and it was published recently, like last December 2020. And here, and again, this is another approach. Here also, we try to develop bioconjugation strategy. Where in that strategy, we introduce the hydrogen groups into the system, and this is hydrazide group was able to combine with these two drugs. So here we develop a combination therapy for the drug development, drug delivery purpose. So not only tissue engineering, we are also working on drug delivery. So, but my concern is like, here also we are using simple bioconjugation strategy. We introduced this dihydrazide group, and then this group was conjugated to dexamethasone, which is a drug for the anti-inflammatory drug. And then we combine doxorubicin, which is anti-cancer drug, with this. So since doxorubicin have very much side effects, so we try to reduce the side effect with the anti-inflammatory drug. So we combine, kind of develop a combination therapy for this kind of application. This was another group, and finally, and very recent, we are also working on the artificial skin. So we are like, I didn't put detailed structure here, but we are working on the polysaccharide based and polyurethanes. And those polyurethanes, we can, by electrospinning, we can develop a nice network which is very flexible, and those kind of network with the kind of thin film we are using for the flexible artificial skin, which could be used in soft robotics as well as in prosthetics in the future. That's the work which is not published yet, but that, like, we are getting very exciting results with those kind of bioconjugation, especially the polyurethane molecules for the artificial skin. So in summary, I would like to say bioconjugation, and play an important role in the development of next generation biomaterial for tissue engineering, for drug application. At the same time, if you see, the organic chemistry is the fundamental to develop those kind of strategies. So apart from these applications, the backbone is like synthetic organic chemistry, where the journey started from this like end application. So thank you very much. This is my lab work, where if you can see in the basic, I started with the synthetic organic chemistry here. The journey started from synthetic organic chemistry. I do simple synthetic organic chemistry to develop bioconjugation of the polymer, and then I bring that to the end applications, the 3D bioprinting and so this is things I'm involved in currently here in Tampere University. Thank you very much for your kind attention, and please ask any question. Feel free to ask anything related to the topic. I'm not sure if I'm not.
Thank you, sir.
Hello. Hello, sir.
Yes, yes.
Sir, there is one question.
Yeah, yeah.
How hydrogel forms cross-linking?
We need some cross-link. It's a kind of, as I mentioned, we can cross-link two biopolymers either by physical attraction or covalent formation. So there are like two molecules, like separate molecules, like hyaluronic acid or any molecule. Two molecules are there. If they are far apart, if we want to combine them, we need some chemistry, either covalent or like physical, like just covalent chemistry or attraction. So for that purpose, let's say we are the acrylation. If you do the acrylation, like they will cross, the two molecule will cross link by covalently by using the acrylation, or maybe you can say thiolene chemistry. You can do the, if you put one group like say azide into the one polymer and alkyne into the another polymer, they will undergo cycloaddition reaction and they will form. So that the overall aim, the two molecule cross link by some way.
Okay, sir. Thank you.
Sir, you have muted yourself. Please unmute you.
Oh, sorry. Yes. Am I answered right, or it was muted?
Yeah.
Yeah, sir.
Okay. So basically, we want to bring two molecules together to make hydrogels, either by cycloaddition reaction or cross-link, like photo cross-linking, or maybe if you put, if you have some coordination chemistry also, you put metal and that bring the main thing, two molecules, two micromolecules should come together, and they should cross-link and they should provide some kind of porous structure. Their water molecule absorb and they become kind of they can mimic the tissue actually. So network is important. If they have the network, then water molecule trap into the network and they become like kind of hydrogel. I mean so the networking should be bring by these kind of cross-linking chemistries. You can design like whether cycloaddition reaction or cross-linking, whatever you like. You chemistry feel free. It depends on the application, what application you are looking for. You need to choose what kind of chemistry, depend on the end application.
Okay. So, we have received two questions through chat box. I'll read that questions. How personalized drugs work?
Yes. So actually personalized, there is no personalized, personalized drug comes later. The thing is like personalized is a concept, personalized medicine, and then using this concept you can develop personalized drug. You can recommend the personalized drug. So that means suppose one patient has having brain cancer, okay, and then since cancer is not only depend on, it depend on patient also. So one drug may work for one patient having brain cancer. That drug may fail for the another patient. Although that drug is known for brain cancer, but it depends on the. It may work for one patient, may not work for another patient. And this is like one drug I'm talking about. There are like several drugs known for the same disease. So suppose 100 drugs are known for that brain cancer. We don't know which drug will work more effectively for that patient. And if we start giving hit and trial, then patient will and you know the property of cancer, they like metastasize and they spread into the body and then they will not control, and if you go to the later stages. So if we want to reduce this hit and trial, what we can do, we can take those cancer cells from the patient and we develop we can develop a small model tumor model, which will be the same as the patient because we took those cancer cells from the patient. That tumor model will represent that patient, and we can, like, if you have 100 drugs, we can simply test those 100 drugs in a single day into that model, and we will know that, oh, this drug will work better for this patient. So instead of giving hit and trial to the patient directly, we can like find the most suitable drugs that like chip system into that model, disease model, and then we can give that drug to that patient. So that's overall called personalized medicine, or kind of, you can say, personalized drug for that patient.
Thank you, sir. Another question is, what process is involved in organ developed on chip?
Yeah, chip means it's simply a small chip actually. So organ on chip, why we are saying organ on chip? Because we are developing a small organ with a small tissue system, which will be like, which will mimic the organ. It will function wise, like if we are developing, say, kidney on a chip, so it will not be exact kidney, but that system, that tissue system, will represent the kidney. So the function wise, physiologically, so physiological function of that small tissue part which is in the chip will represent the kidney, so that we can test everything whatever on that chip that will be applies for the kidney also. So the chip, in the sense, we are trying to develop, why we develop on the chip, because chip has several system, like sensing system into that bottom of that chip, and then we can like put hydrogel onto that chip, and then there are several other we need to develop micro channels with the help of like microfluidic technology, because we need to flow the fluid which is like as a body fluid, right, so that it will be mimic the organ. So we have to have micro channels, and so that the chip design should be like, it should include everything which is needed to for the growth of the tissue. It should have the hydrogel which provide a kind of environment for the cells to grow, like we have extracellular matrix in our body, similar. So instead of extracellular matrix, we will use the hydrogel to replace that, and then we will, instead of the like veins and all we have in our body, we will have the microfluidic channels which will provide the fluid for the cell growth and all those, and will provide nutrient, oxygen concentration, everything. So that's the reason we like call as this complete system called chip. So we need like chip and kind of micro channels to provide like nutrient to the tissue growing there, and we also need like oxygen, some channels to provide proper oxygen concentration. So it's a combination of many technologies together, so develop a chip basically. And we need to have some sensing technology at the same time to sense those and to characterize those whether they are working properly or not.
Thank you, sir. We will take one more last question. So the question from the participant is there any application of this bioconjugation in food sector?
Yes, because the most important application is, I mentioned, like lab grown meat. So we can like, if you see the carbon emission is too high because of slaughtering the animals, but because one animal's growing took a lot of is responsible a lot of carbon emission. So lab grown meat is a great future if you see from food industry perspective. And there are many other applications to test other, like develop some system to test many other drugs which are not toxic, or maybe some other kind of chemicals which we are going into the food industry, that also can be checked by this organ on chip, body on chip technology. But the most important advantage I can see in food industry is the lab grown meat, which can replace the actual animal slaughtering.
Okay. So
Thank you.
participants have a lot of questions, but due to this time limitation, we will mail you their questions. So we will continue with our conference schedule.
Okay, thank you for inviting me, and it was pleasure for me to present this strategies and my work to the young minds. Maybe some of them will maybe go and work in this field in the near future sometimes. Thank you.
Just a minute, sir. Our some protocol is there.
Thank you very much, sir, for sharing your insightful knowledge with us. Now it's time for break, and we would like to request all the participants to join the session at 12 p.m. for next invited talk. Thank you. Join the session through the same link. Thank you all.
Thank you, sir. Dear participants, we have our next speaker with us. So we will start the session in a few minutes. Welcome, Dr. Patil sir. Dear Patil sir, we are participants. We are starting the session. Patil sir, before we begin, we have some protocol. One of our faculty member will introduce you. Then we will begin.
Yes, please. By that time, can you, some of you at least switch on the video? I would be happy to see the faces.
Dear participants, actually, sir, we have, some of them are starting video, but they are due to some bandwidth problem. We have put some restrictions on their voice and video thing.
Yeah, no problem. Okay. Go ahead.
Okay. Hello, am I audible?
Yes.
Okay. So good afternoon to everyone. It is my honor to introduce our third resource person, Dr. Ajay B. Patil sir. Dr. Patil has completed PhD from Savitribai Phule Pune University, Pune, and Bhabha Atomic Research Center, Mumbai in 2013. After the award of PhD, Dr. Patil has completed his first postdoc research work at University of Bologna, Italy. In 2015, Dr. Patil joined to Paul Scherrer Institute, Switzerland as postdoctoral research fellow. He is associated with Paul Scherrer Institute since 2015 through various posts such as project management and scientist, etc. Currently, he is working as scientific collaborator at EPFL PSI, Switzerland. Dr. Patil has 9 years of professional international research experience, and he is expertise in analytical chemistry, including spectroscopy and chromatography, inductively coupled plasma optic emission spectroscopy, and mass spectrometry. Dr. Patil has successfully executed projects in precious and critical metal separation, small molecule synthesis for separation applications, hydrometallurgy, chemical process development, scale-up and prototype development, metal chemistry for platinum group, rare earth, and actinide. He has implemented new technology and entrepreneurial activities at Paul Scherrer Institute, including proven soft skills in pitching process, economics, partnership and business development, milestone planning and execution. Furthermore, Dr. Patil is also working on scientific reporting, extramural fundraising, IP management, and its commercialization. Dr. Patil has presented his research work in various conferences and received much more appreciation through best paper and presentation awards, etc. He is a reviewer board member of scientific journals such as RNC Advances, Minerals, Applied Sciences, and Molecules. He has published 16 research articles in international peer-reviewed journals with total 366 citations. Along with this, 1 European patent and 2 book chapters to his credit. He has partnership with 4 industries and government authorities and raised equivalent to $1 million funds as award and grants, including 2 European scholarships. With this brief introduction, I request Dr. Ajay Patil sir to deliver his talk on the application of chemistry in the sustainability. Thank you very much, sir.
Thank you, Dr. Mahire. Can I start, if it is okay?
Yes, sir, you can proceed.
Yeah. So, hello everyone. Thanks for joining us today in the CPCS session. My talk would be on topic of applications of chemistry in sustainability. So as I have mentioned, that I have a double affiliation. I work for Paul Scherrer Institute in Energy and Environment Research Division, and also for the Swiss Federal Institute of Technology. Here I'm engaged in environmental engineering school. So what is my research group exactly doing is that we are expertise in online trace metal analysis, also thermal processes for the material recycling, material processing and purification. Our institute has a state-of-the-art structural analytical facilities, and this helps us to develop new processes for safe treatment of different feedstock materials, and that is why we are very powerful in development of materials for ecology and economy. And my own specific subject area in this department or in this group is about critical metals for energy and environmental applications. And all this is necessary to generate the alternative energy pathways in general, which should be environmental friendly. So we do chemistry at solid gas and solid water interface in nutshell. So what would be the agenda of the talk today is that I will briefly mention within the scope that what is going on in the around in the economic world in terms of sustainability. Then I will tell you a brief story of chemistry and technology for our economy and environment, and about sustainability, which is the core topic of my talk today, what it means for us and for future chemists, and what implications does it have and responsibilities does it have as a professional on us as a chemist. And this will be followed by some examples by market leaders, and I will briefly mention in few slides how my research group is contributing to this mission. Then finally, I would convey some thoughts and maybe inspiration if I could, or if I will be successful in next 40 to 50 minutes to take you home. So in a nutshell, this won't be a sophisticated chemistry lecture today. And before we dive into story, let's play a little bit. This is a quick quiz we have to go through. I want to remind that it is a voluntary quiz and participation is not mandatory in it. It's up to your own willingness. And this is just because we don't want today's talk to be monotonic. Even if we cannot meet personally, we should get a little bit flavor of each other's and of today's topic. So this is an attempt to cheer ourselves up after hearing earlier two sessions. So I would request you, whatever device you are using, either computer or cell phone, go to menti.com. It will ask you a code. Put this 8-digit code. I will give you roughly 1 minute to log into the site. Write your short name. You have a choice. You can write number or no name. And you will have 20 seconds to give a correct answer of the quiz. And the person who will respond in shortest possible time will be the winner. And if everything goes well, I can show you who is the winner. So are you ready? So I could see so far 4 people are joining. 5, 6. And I will start the quiz. Don't forget to respond as fast as possible. Only 5 questions. Okay. So what is the most important aspect for developed human society? economic growth with commercial activities, economic growth with and ecological well-being, environmental friendliness without commercial activities, political, economic, and versatile growth. Respond. Time's up. So right answer is economic growth and ecological well-being. 5, most of you have responded correct. So Komal is the winner for this question, who responded quickly. So here is the next question. To which discipline sustainability topic belongs to? Perfect. So 5 people have given correct answer. So Pingu is the winner. Good. So question 3. Which arrived at last? Aeroplanes, mobiles, electric cars, or television? So mobile phones is the correct answer. Electric cars are there since 1920. Sachin is the winner. Second last question. Minamata disease is due to the pollution of. Perfect. Most of you have given correct answer. Let's see who was fastest. Sachin was fastest again. And the last question. Where the chemistry does not play a role in product life cycle. Tricky one. So perfect. So Rohin is the winner with 3070 point. Congrats. So I will stop this one now. Perfect. So let's dive into story now. Back to work. So what is this about, the sustainability and what is going on in the world around us? So the 2030 Agenda for Sustainable Development, which is adopted by all United Nations member states in 2015. It has decided the 17 Sustainable Development Goals, and it requires an urgent call and action by all countries, whether developed or developing, in global partnership. And this is necessary because they have recognized that ending poverty and other deprivation must go hand in hand with the strategies that improve health and education, reduce inequality, and spur economic growth, all while tackling the climate change and working to preserve our oceans and forests. So many holistic goals, but also a lot of research and business opportunities, because this will reshape the world towards 2030. And why it is relevant for us as a chemist, or why it is important for us as a chemist, because you see that all the chemical societies are aligning themselves with these sustainable development goals. Here is an example of ACS, and as a chemist, how we could contribute, or which are the sustainable development goals for us, to which we could contribute ourselves. And you will see that we could contribute as a chemist to zero hunger by agricultural chemicals and preservatives, good health and well-being, of course, pharma and diagnostic industry, clean water and sanitation, affordable and clean energy based on the new and advanced materials, and as well you could see the industry's innovation and infrastructure, about the new products, about the more efficient and let's say profitable products, responsible consumption and production. This would be necessary that we use the resources we have judiciously and wisely, and that is why by using all of this goal we contribute to sustainable climate action. And you see here that ACS has characterized different statement in different categories, right from sustainability in chemistry enterprises up to chemical risk assessment and regulatory decision making, that whatever the industries and researchers are doing, they should do the things rightly. And here the topic critical materials is the one which is my core area of research. Just to give you an example, also the societies like RSC and Elsevier are focusing on the green chemistry and sustainability or circular economy more and more. And this is a viable approach and being developed around the world very rapidly. So what is the story of chemistry in our economy? I will give you two examples of industrial sector where the chemistry is used as a driving force to develop finished or fine products. For example, in pharma industry, we take natural resources, we do chemistry and biology, and from starting from 10,000 molecules, we can get one drug compound, which is marketed as a drug in the end. So, except the environmental impact, it has nearly 802 million US dollar cost over 15 years. The another example is which is also directly linked to our day-to-day life is here we could see the gadgets or electronics industry. So we mine the raw materials, we do the process chemistry, then we do the solid state chemistry and physics, and we have our lovely gadgets which are in our pockets. And millions of US dollars are spent on resources, R&D, and product development Just to give you a precise definition, whatever gadgets we have in our pockets as a smartphones, they have at least 27 metals as a raw materials used in them. So what exactly we mean that we develop science and we do engineering and technology development, and what implications or meaning it has in manufacturing or product development world. So, and how they are interlinked with each other. When we talk about science, technology, engineering, and mathematics, then the easiest definition I could find is technology is the engineering of science, and manufacturing engineering is the scaling up of the engineering which is developed out of the science. And this is to enable the efficient and economical mass production of finished good. So it is inevitable to avoid chemistry out of any life cycle stages over here. So how we are going or how we are developing this nowadays, I will give you an example with a metal industry, how we are driving current manufacturing processes, how the metals determine our life. You could see on left hand side that metals we use today, a short term use would be our cell phones, of course, a small gadgets or commodities we are using. A mid-term use is our cars, our laptops, our different tools. And long-term use is, of course, big shipping equipments and bridges, wind turbines, or buildings, whatever we use. And just to give you a perspective, what impact does it have on a scale of chemistry which is done, or a scale of environmental impact it could have. From 1980 to 2008, the global demand is increased by 87%. You could see here, 1980 to 2008, and up to more than 6 billion tons right now. And this demand is driven by building up of new infrastructure. We have new buildings, new bridges, and new cities, and enlarging cities continuously. Electronic revolution, everybody has a gadget. It's a totally altogetherly different world we live in. This is also why we could talk to each other or listen to each other today. And shift towards renewable energy is driving this demand of metals even much more, even on much more scale. And this results in declining ore grades. The more we excavate from earth, the more lower quality grades over we have to exploit as well. Resource scarcity, and that is why the pricing is increased. That is why we have overall inflation around. And very important is the environmental impact. So we are damaging environment and also the human lives severely. When we see this metal life cycle, you see that we do the raw material extraction, mining and refining take nearly 77 to 8% of global energy supply. You can imagine what impact it has on the ecology. And it also have more than 70% greenhouse impact at this very much primary resource extraction stage. Then we refine, we manufacture the goods we want to use. We use them during the product life cycle, and at the end of the life, we dispose them. So this is how the linear economy model works, that you extract the resources from the nature, you manufacture the commodities and the gadgets or appliances you want to use, or medicines, you name it, whichever product you want to use. And then after end of use, we dispose it. And this cannot continue forever. That is why we have the option of circular chemistry, that we collect and use the waste, we maximize the atom circulation. And this will also help us to optimize the resource efficiency. And this is why we can then strive for energy persistence. And this will also enhance our process efficiencies, how we do the activities in R&D, in manufacture, in controlling things, and no out of plant toxicity. Absolutely, because we have to preserve what our ancestors have given to us, and we have to make sure that we are transferring it to the next generation, that it is worth to live for them. and they target optimal design, access sustainability, apply ladder of circularity, whether the minimization could be done, whether the long lasting products could be done. Sell service, not a product, to minimize the resource use, reject lock-in. It is not necessary to use entire big components. We can also replace small components in big gadgets. Unify industry and provide coherent policy framework so that they can match with each other's standard and there will be minimal losses. And why we have to do all this? Of course, there is a reasoning from global to local level. This is a very interesting data I could find out. If you see the frequency of annual rainfall in Jalgaon district between the years 1901 and 50, the 80% of the years were above average rainfall, and maximum temperature which could reach, you could see here, was 47.8 degree, even if it was a era before thermal power plants. And now what we have nowadays is that temperature every time above 50 to 52 degrees Celsius, at least in May each year. And there is steady decline in rainfall each year. We have lesser incentives out of conventional agricultural businesses. That is why we are roaming around the world and working and not staying at homes, right? And if you remember this increase in temperature, which is nearly, let's say, 4.2 degree, and you remember your high school lessons that for every 10 degree increase in temperature, the rate of physiological and process reaction doubles. That means it has an impact on our physiology, it has an impact on our surrounding, and we have to do something. So does it mean that we have to stop our power plants? Does it mean that we have to stop our economic activities? No. We don't have to segregate the economy from environment. We have to combine them and to develop the sustainable ways. Instead of doing the things right, which we are doing since ages, we have to start doing right things now. So management is doing things right, means whatever protocol is, we have to follow. We don't want to think out of the box, but leadership is doing right things, that you think sustainable, you think long term in the benefit of everyone. As I have said in the scopes slide, that I will show the few examples of the market leaders, how they are developing the circularity or circular economy concept in their businesses and processes. So this is an example of petrochemical industry. You could see that they use different resources, whether it is gas, biomass, power, oil, waste, or salt, water or salt. And their end users are agriculture, automotive, coatings, building or construction, durables, electronics, packaging, and water industry. What they have done is they have combined both the product life cycles on resources and end user sides. And now they are developing sustainable processes by reworking on technical materials and recycle them, refurbish and remanufacture the plants or the machinery they are using, reuse and redistribute the material. Sometimes the catalysts are depleted, but you can regenerate them and you can give them back to industry, chemical industries or pharma industries, and then maintain, let's say, appliances and chemical engineering equipment to retain the processes over long term. And of course, recover the energy via production byproducts. Next example is a very famous industry, BASF. So if you see their business was working, that they use the resources. In the gray line is their linear model, how they work in that industry. They take resources, they do raw material production. Then there is a BASF production of secondary raw material. They give it to the customer, whether they want to build cranes or cars out of these raw materials. And finally this customer industry will sell the products to the end customer, which is business to customer mechanism, and after use it will be disposed. But what BASF has optimized now, you could see in this green lines. So from raw material to BASF production, they will recycle whatever is the production waste. From BASF production to the customer production, they will establish a take back system, that whatever which is not used by the customer, he doesn't have to throw it away. They can take it back and they could use it in next batch of production or other commodities. And at the end of the use, they could convert it into compostable bags or additives for this sort of customers, or they will convert it into the resources once again by recycling. So what they have gained by adapting this approach as a chemical industry, so they could use residual as a raw material once again, and lots of solvent recycling could be done, and this has even gained cost and economic incentives for them. And the efficient use of byproducts could be done with this take back system, and chemicals which are enabling resource savings and of course economic savings for them. And also they focused on chemicals which could prolong the lifespan of the products. Finally, the most important part is the biodegradable products, compostable bags, and biomass balance in the nature. As a chemist, now we will wonder how we can contribute as a chemist in this thought and in this new development approaches. So how we could contribute as a green chemist? We could develop the processes with use of minimum solvent, minimum catalyst, and let's say a UV light, which is the visible light, which is easily available source with minimum energy requirement. This is my favorite example. And also the overall green synthesis approaches, like we could prevent waste in our chemical reactions. We could maintain atom economy to have a minimal losses and environmental impact, less hazardous synthesis, safe chemicals design with minimum steps, benign solvent and auxiliaries use, energy efficiency, renewable feedstock, reduced use of derivatives, catalyst design for degradation. We should make sure that whatever we are developing as a product, as a new synthesis molecules, should degrade in a natural pathway. Then real-time analysis and also so that to minimize the development and the manufacturing losses. And inherently, we should strive to develop safe chemistry as much as possible. In the fuel industry, which is much more impact giving, nearly 10% environmental impact come from this industry alone in the world. So we can develop synthetic oil molecules which are more homogeneous, you can see, as compared to the conventional or natural one. So we have better process control, and this could be very, very efficient for engines and future generation vehicles. And overall, we should try to synthesize new and molecules, fuel molecules with biological origin. How it gives impact if I am a physical or material chemist or a physicist. Of course, there is a demand of new green energy materials development, which should either generate energy or save or recycle or convert into another form. So a lot of new materials and sensors could be developed, and which could be then helping us in maintaining this lower environmental impact and could increase the profit for industries. Finally, as an analytical chemist, how I would contribute? I would use the GAC approach, which is green analytical chemistry. We will strive for miniaturization. We will strive for eco-friendly solvents, and as well micro extraction, reduction in analysis time, less solvent consumption. And quality by design means we use a design of experiment approach. I was wondering and astonishing that even for our research faculties, such courses are not included, which reduces the efforts and use of chemicals on much scale, higher scale. Analytical target profile, we should know what we are doing by targeting the right product and profile, so we can minimize the losses by processing it in minimum steps. No revalidation required. If we have a reliable process over the years, statistical analysis will help in the minimum steps. Quality before testing. If we optimize the processes which could give optimal qualities, then we don't have to test them again and again. We have to take quality and processes under control. And finally, design the space, which should be sustainable. And the applications of this could be mass spectrometry, HPLC, vibrational spectroscopy, and gas chromatography. In nutshell, we use 3 R's: reduce, replace, and recycle. But analytical chemistry could go far beyond this. How? We would see now. Yes. So how my group is now contributing to this kind of chemistry by the rare earth elements chemistry for sustainability. We have one solution which could target at least 5 sustainable development goals, which I was explaining you. The goal number 7, which is affordable energy and affordable and clean energy, because we focus on materials which are used in clean energy sector. Industrial innovation and infrastructure, because these are the materials which are driving the lots of high-tech industries. Of course, sustainable cities and communities. If we provide appropriate waste management and recycling infrastructure, this is what we need for future generation, because per capita use of resources and gadgets is very high, and it would be much higher in future. Then responsible consumption and production, how to maintain in minimum resources, how to recycle resources, so that we should have minimum climate impact and we should preserve our ecology. So what is my core research area? It is the chemistry of rare earths or lanthanides in general. These are 17 metals which are essential component of almost all the modern electronics, whether you talk about your cell phone or it is satellite in the space. They are everywhere. They are the driver of industry 4 revolution, whether we are using magnetics in e-mobility or in MRI, in power generation with wind turbines or with hydropower generation. They are in metal alloys, in the batteries, and in superconducting alloys, in defense and in satellite communication system, in chemical industry, particularly in catalyst for petroleum refining, in catalytic converter, fuel additives, air pollution control, in glass polishing industries, very powerful and let's say very sophisticated conditions can be achieved, and such glasses could be used at high temperature, at high pressure, if we use rare earths in them. And of course, ceramics to develop capacitors or sensors or colorants, scintillators or refractories. These materials have revolutionized this sector in real sense. And of course, the phosphors, how we could hear or see each other's today via this virtual meeting is because rare earths have revolutionized our electronics. You remember that we were once using landline phones, then we were having the cell phones, and now we have smartphones. This is because of this higher performing rare earth metals and their properties. So why this is the topic relevant for sustainability? Because our green technologies are not so green in real sense. The reason is that there are a lot of radioactive and toxic byproducts. So our green technologies have a dark side. The mining of raw materials generated a byproduct with huge environmental impact. But circular economy approach could help solving this. So I will show you a classic example that how the circular economy could be adopted as a chemist for societal as well as well-being of the industry. So we mine the raw material, then we convert them with physics and chemistry approaches of materials development. And these are the gadgets for our tech-savvy generation. And we use each gadgets 2 to 4 years. You know very well, maybe this is your second or third or fourth smartphone. Everybody has to upgrade with developing technology, and we generate a waste which is landfilled. So what we have to do is to reduce the negative environmental impact of mining of rare earths because they have radioactive byproducts. Reduce negative environmental impact of disposing electronic waste here because it is causing, our gadget use is causing hardship to environment and human lives on both sides of value chain. And reduce the strategic supply dependency and geopolitical risk. Why I am saying this? Because of this reason, because most of the rare earth supply is controlled by a single mineral exporting country, and that is why you could see that always there are supply quotas and little bit uncertainty in supply chain. And this is also used as a let's say leverage in the trade war. This is reflected in many articles, and there are many articles also coming, and a lot of media traction is there, a quite hot topic. And this is why it is also mean if we develop alternative rare earth metals value chain or supply chain, it could help to protect the big investment and the businesses in the rest of the world. And of course I'm a Swiss researcher, so unless and until there is a let's say incentive, we won't involve ourselves in doing such activities, because the aim is not only academic. Of course we have our academic interest, but also economic interest. So in this graph you could see the demand ton per annum of rare earth oxide, and you could see that over the years the Chinese demand as a mass manufacturing hub is increasing. So what they could export to the rest of the world is decreasing. So that is why they could not match the rest of the world demand, and there is a deficit. And we thought we must do something over here. And the another thing is sustainability. You could see that importance to the clean energy here versus supply risks. So the metals which I am expert in, neodymium or dysprosium, europium, yttrium, and terbium, they have a highest importance to the clean energy, and they have highest supply risk. And all these metals in this kind of end of use resources or feedstock are landfilled at the moment. This is very sad part. That is why we got attracted with this nearly 13 billion US dollar market, which have astonishing growth rate. There is a big deficit, so ideal time to enter the market, and this is ideal impact investment opportunity for your time, for your talent, for your money. And as a chemist, you always have your curiosities and passion. So as an analytical chemist, and during my PhD, I was trained, and since beginning I was having a lot of interest in block elements, mostly actinides and lanthanides. I did most of my PhD work with actinides as a part of my work with Bhabha Atomic Research Center. And in my post PhD career, I am focusing on lanthanides. These 15 lanthanides plus scandium and yttrium means 17 rare earths, just to give you a proper definition. And why this chemistry is challenging, why it is not everyone's job, because of their inherent nature. If you see that they are placed between the row second and third in periodic table, that is why size decreases from left to right. So from lanthanum to ytterbium or up to lutetium, to be precise, the size is decreasing because of addition of the electrons in the same F subshell. And this is a very famous effect called as lanthanide contraction effect. So if you see the same periodic table as a atomic radius in picometer, you could see in the rest of the periodic table the sizes of atoms in picometer are different. That is why their chemistries are different and they are very peculiar. But in case of rare earths, you see the sizes are nearly same, and the chemical and physical properties are always determined as the effect of atomic sizes. This is determining the interaction and reactivity and also the physical property of elements. That is why rare earths are virtually similar to each other. And this is the reason why they could not be separated from each other so easily with conventional approaches. So that is why because of their similar size and properties, it is very difficult to separate them and to achieve them in high purity and to use them in industry. And not so many industries or researchers are specialized in it. But there are also opportunities, because I told you that there is subsequent filling of unpaired electrons in F subshells. That is why there are ample amount of unpaired electrons, and which gives them an impressive magnetic and optical properties. And this has huge technological applications. That is why we could transition ourselves from let's say cell phones to smartphones, from a conventional television or computers to the laptops and the flat screens, because these materials have very powerful properties as compared to the transition metals which we're using earlier in the past. So now that is why we decided to go for a new purification technologies based on my existing expertise and professional competencies. So we want that the separation process should be quicker, efficient, and environmental friendly. And this is the core competency of my group, that we use e-waste. We convert it by hydrometallurgical process to 99% pure metals, and we transfer it back to the economy so that they could help in energy production, reduction, efficiency, and catalysis systems. What is this chemistry about? Is that we are developing molecules which should be selective by using hard soft acid base theory, because rare earths are hard acids and they bind with the hard bases. And we need lipophilicity, because they should extract or purify the metals. And of course, all these molecules should be compatible with high acidities, because all this chemistry is done in high acidities. So we designed and synthesized a number of selective molecules. You could see that we did permutation and combinations. We did develop a series of structure and activity relationship for this application, and we used it for actinide extraction. Such approaches could be explained for rare earths recovery. Our current processes are based on these two different ligands, because we wanted to develop commercially viable process, so we cannot use a sci-fi chemical ingredients. And you could see that the complexation for this rare earths happens with ligands, and after ion pairing they go in organic phase and get separated from rest of the impurities. And this is a typical extraction approach which we use to save the impact due to our own ingredients and acidities and organics we use. We also develop some supported liquid membranes based processes. And in this process, the field solution, which has a mixture of metals, could be exposed to the membrane which is containing this synthesized ligands, and in strip it selectively then transfers the metals which we want by maintaining appropriate conditions. This is the schematic representation how we do it actually. So we do it in this way that the metal get bound with the ligand, it transfers through the membrane and it reaches the receiver to the receiver end selectively or to the strip end. And then we do assaying by taking samples, and we do a clear monitoring of the metals, how they are getting separated and how they are getting purified. And then we get a meaningful data and better process control, how to separate them in what conditions. So our current process is based on recycling these secondary resources to get 99% pure rare earth products with safe waste management. And this is a hydrometallurgical process which is patent pending at the moment. And this will enable us to exploit the nearly 2,600 tons of rare earth content in the e-waste in Europe alone. And you could see that this has received traction in a very high impact publication as well as in the European patent application. So just to show you example how we purified these kind of strategic metals and difficult purification. So the initial feedstock which was containing nearly 0.4% rare earths could be enriched to 99% by using a different chemical conditions and process approach. So overall process, you could see that we could convert such kind of waste in more than 99% pure rare earth products such as terbium, europium, and yttrium for the first time from the secondary resources. And how it runs, of course, this is a totally commercial project. How it runs beyond the test tubes, because we were interested in much more conventional activities. So I have to stop my pointer. Oh, sorry. So this is how the process runs in reality. I hope everyone could of you due to bandwidth could see this video. This is my lab and how we are doing the piloting of our process, which I showed you in earlier slide. And this then gives us access to high purity metals, which could then go to the front end market once again. So, and what impact it will have? Of course, this is not only the research and technology development, but also the business and innovation. And it is related to the sustainability and climate impact, of course. This will help us to reduce impact. For every recycled ton of rare earths, it will avoid nearly 1 to 1.4 ton of radioactive waste and equivalent amount of greenhouse gas impact. So that is why we are very proud that we are developing such systems. And to conclude today's talk, I will give some conclusions and perspectives that sustainability could be brought in critical rare earth supply chain. I have shown you the real example how the circular economy could be applied for chemical process development. Effective separations of rare earths, yttrium, europium, and we are very proud that terbium processing could be done in only few facilities around the world, and we are one of them. Easy to scale up and commercialization was our aim since beginning of development of this process. And this process would be commercialized by a new company, which will be spin-off out of Paul Scherrer Institute called as Remeretech. And we used e-waste as a resource by urban mining, which will give low environmental impact in future. And of course, the future belongs to sustainability and interdisciplinarity. We can delay it, we cannot avoid it. And there is always a way to grow economy without sacrificing the ecology. Now this gives a bonus slide. As I mentioned that I will try to give you some thoughts to take home. So we know that sustainability is everyone's responsibility. Just to show how we grew as a humans in last nearly 300, 400 years. In 1700, we were using only wind and hydropower. Our resource footprint was very less. We started using steam in 1800. Then we started using fossil fuels in 1900. Then we are going to the green energy sector now. And you could see that the number of resources and metals we are using are increasing on very, very high number. Be careful that this rare earths means 17 metals here in these two dots, yellow dots. That is why if we receive or use more, we are expected to contribute and care more. Because as Mark Twain said once about the land use, it also applies for the metal use. God is not making them anymore. They are in equivalent amounts since the Big Bang. Finally, I will rest my case with the quote from Albert Einstein that those who have a privilege to know, they have a duty to act. And we are very proud that we acted. I would like to acknowledge my funders and supporters who have financed most of my work and research and business activity. And of course, a sincere thanks to Dr. Yevle and entire CPCS organizing team for hosting me today. And I would be happy to take some questions. Thanks.
Thank you, sir. Now the talk is open for the discussion. If you have participants, if you have any question, please send us through chat box so that we can read them here. Till that time, I have one query, sir. So, what is so difficult in this rare earth metal that there is very little research in the whole world? What makes it difficult, them?
Yeah, so the answer to this question is a twofold. First is because in the primary resources, rare earths, so actinides and lanthanides lie together in the ores. That is why you cannot have rare earths separately. You also get some actinides which are radioactive. That is why it is not everyone's job to play with this chemistry. And then the second thing is that this chemistry is inherently difficult because of the lanthanide contraction effect, because the 17 metals or elements have nearly the same properties. So it is very difficult to get them in high purity. That is why it is very difficult to control their properties and proportion.
Thank you, sir. Dear participants, please send your questions. One question is there, sir. How does the carbon chain affects the ligand properties during the extraction?
Yeah, so the extraction is basically the phenomenon that you have in a liquid many metals and impurities, and if you want to separate them, you have to take them out of that phase, and out of that phase means it should be immiscible, that you could separate it, otherwise the separation principle could not work. That is why the carbon chain has to be longer, so that the metal ligand complex should be soluble in organic. Because the metal ligand complex is soluble in organic, this is an inherent property given by the long carbon chain. This is why the molecules are designed in such a way.
And what about the effect of heteroatom substitution during the carbon chain?
Yeah, this is as I have mentioned that all this chemistry is done in very high acidity, almost in concentrated acids, because these are very hard metals and we can't do their chemistry on ambient condition. It is always done in harsh conditions. So that is why if we want that such kind of chemistry has to be done in this harsh condition, the ligand should not react with acid and it should not have a high basicity. So we introduce heteroatoms to control the basicity of the ligand molecules.
One of the participants has asked whether any byproducts during this process.
Yeah, so the byproducts are, we are mainly focused on the rare earths because this is my own specialized chemistry. But there are other byproducts such as platinum group metals and also cobalt, vanadium, which could be recovered.
The participant is asking whether the byproducts are useful for, means harmful to environment or not.
No, not at all, because all the products are high boiling or high end metals. So nothing goes out of the process. Everything is under control.
Thank you, sir, for your precious time, and thank you participants for this fruitful discussion. So if there are no more questions, then let us thank Dr. Patil for this wonderful lecture on sustainability and giving the new views about the sustainability. So over to Birun Madam.
Thank you once again, sir, for sharing your insightful knowledge with us. Now, valedictory session will start shortly. Please be with us.
Thanks, everyone. Thanks, organizers.
A very warm welcome to the valedictory session of International Conference CPCS 2021. It is my proud privilege to welcome Professor S.V. Patil sir, Vice Principal, Pionahata College, Bhusawal, and President of valedictory session. I also welcome faculty members, academicians, research scholars, students, and dear participants who have registered for this international conference. Now I request C.H. Sarode sir to deliver the valedictory address. Over to you, sir.
A very good afternoon to everyone. Dignitaries on the dais, distinguished faculty members, heads of various departments, research scholars, and dear participants. It gives me a great pleasure to present to you a summary of International Conference CPCS 2021. We hope that, considering the rural background of the institute, this conference has served as a platform for the college level researchers and students to learn and know about recent advances in various fields of chemical sciences. I hope that you may have enjoyed the session of one-day international conference. The conference was inaugurated by Sri Sanjay Kumar Nahata, Treasurer of the Education Society Bhusawal. Around 155 participants have registered for the conference. During the 3 sessions, eminent scientists and academicians gave invited talks, which includes Professor Rajendra Zope, Texas University, USA, Dr. Ajay Patil from Switzerland, and Dr. Vijay Singh Parihar from Finland delivered the lectures. The topics discussed includes density, functional theory development, synthetic organic chemistry, in progression of bioconjugation strategies, applications of chemistry in sustainability, etc. We hope that the variety of topics discussed in the conference will help research scholars and newly recruited faculty to initiate their research areas. I thank all the delegates and participants for taking part in the conference and making it a great success.
Thank you, sir. I request participants to share their views about the conference. So I request you to unmute yourself and speak for us.
Hello. Hello.
सर
Yes,
येतोय
sir.
आवाज
You are
सर
audible.
येतोय सर
You are audible,
Ah,
sir.
the chemistry department of Bhusal Arts, Science and Pure Nata Commerce College has organized such a wonderful international conference. Whatever the resource person delivered, it's a galaxy in chemical sciences. Chemistry is an important part of our life, day-to-day life. Without chemistry, we cannot survive. And whatever the researches going on is important. Dr. Zope, Professor Zope, Professor Ajay Patil, and Professor Parihar, these three resource person gave a valuable time for such a conference on behalf of this college and the institution. Uh, from the bottom of my heart, I thankful to all these three resource person, and also thankful to the chemistry department, Dr. Sachin Nevle and Professor C.S. Sarode and all the members of the chemistry department organized such a well and good conference. I hope all of you enjoyed this conference and took and also inspired some knowledge, and this conference gave inspiration for doing such type of the research work. So again, I wish thanks to all. Thank you.
Thank you, sir, for your insightful remarks. Now I would like to invite Dr. Ajay Kshisagar, sir, to deliver vote of
Thank you, madam. Good afternoon to all. It is great honor and privilege for me to propose a vote of thanks on this occasion. I am thankful to all the participants for coming to Bhusawal Arts, Science and Pionata Commerce College, Bhusawal, to attend the international conference. We have been fortunate to have some of the eminent person from academia and research institute. I am sure that the participant must have benefited by attending this conference. I am sure that CPCS 21 will continue to get generous support from various organizations in the future also. I am thankful to Honorable Dr. Mohan Bhau Falak, President and all directors of Tapti Education Society, and Principal Dr. M.V. Vaikole Madam for giving us an opportunity to hold CPCS 21 at Bhusawal Arts, Science and Pionata Commerce College, Bhusawal. I am very much thankful to Honorable Sri Nataji for sparing his valuable time for inaugural ceremony. I am also thankful to Professor S.V. Patil sir, Dr. B.H. Barate sir, Dr. Edi Goswami sir, and Professor Yeni Bangale sir for their valuable guidance. I am very much thankful to Advisory Committee for their continuous support and advices which have greatly helped towards the successful organization of CPCS 21. I am also thankful to Professor Rajendra Professor Dr. Ajay Patil sir and Dr. Vijay Singh Parihar sir for accepting our invitation for this international conference. I am also thankful to all organizing members and non-teaching staff of chemistry department who has greatly helped us in organizing the conference. We are grateful to Dr. Jiarwani sir for providing his code for generating certificates for this conference. We are also grateful to Harshar Patil sir for technical support and Prashant Patil sir for publicity. I once again that everyone whose contribution has made this conference a successful conference. With prior permission of the session, I declare that the valedictory session is over now. Thank you very much to all.
Hello.
Thank you.
Hello. Hello. After verification of data, we will circulate your certificates on your email. All participants are requested to fill the feedback form. Link will be shared in the chat box as well as on Telegram group. Thank you very much.